your M is just, it doesn't matter what it is. For any value of M, that's true. Small, large, it doesn't matter.
Oh, for any value of M.
For every value of M, A, and B. For every value of M, A, and B. When you make a circle.
You can share the program.
But does it matter? But does it matter whether the
Awesome. I have, yeah, I
I don't
have,
remember what people talked about.
For every circle.
yeah, I
it goes
have
forward. It's a topological.
I
circle.
have one, yeah, probably, I have it's okay, I can find it probably too.
I'm struggling.
I'm sure people wanted to talk time to me, maybe during the next coffee break.
I'm sure we probably satisfied. We just have to look more we just want to see. I
I
want
want
to
to
see
say things that are more constructive. Maybe you can do it as a small consistency check. Hilariously interesting. Read the question about the domain one. Okay. You're like the question about the conjectures. You have a comfortable copy.
And you would but I mean, it's true. One thing is a lot of yeah.
Everyone have no doubt that we're satisfied with this.
What is the reason the data prime goes like n squared and not one?
Should I continue? It could be that it's kind of
an artifact of the way you because it's at the very end, all these classes of the so it has to get the what it means is it's kind of parameter behavior, which is different. So
we haven't published it. I think the final.
Okay, the next speaker is Mike Dine, who's going to tell us about confinement in real experience.
to understand it. Sorry.
Okay. So the title is a little. Because I'm not going to claim the Clay Prize based on any of the marks I'm going to give. What I would like to convey is the notion that we might be sort of on the edge of some understanding. Confinement, starting with SUSY QCD. And so first of all, I want to thank the organizers for this second opportunity to speak with the SUSY conference. I don't remember that well what I spoke about in 2000. I'll have to go back and look, but it wasn't this. And I think as I said, I think our thinking is our focus has changed. My focus here too. It will be less on how supersymmetry might not be realized in nature, but on how supersymmetry is a tool for understanding questions in quantum physics. So that said, what we have in ordinary QCD supersymmetric QCD, an understanding of confinement in the existence of a mass gap. So these are really starting with the work of Seiberg and Witten and others. We understand the existence of the mass gap and confinement are readily established features of many n=1 supersymmetric gauge theories. This is the case in particular for gauge theories about matter fields and gauge theories of only massive matter. In exploiting tools such as holomorphy, it is possible to study many aspects of the problem, such as the rule of monopole condensation. And it's natural to ask whether these results can be extended to demonstrate confinement in non-supersymmetric theories. One could start, for example, by taking a supersymmetric gauge theory without matter and then introducing a Gaugino mass term. Due to the mass gap, for small Gaugino masses, both the mass gap and confinement might be expected to persist. And to elaborate that slightly, because it's a question you might ask in some of my later remarks, in the sorts of effective action description that we saw this morning and yesterday in Hitoshi's and Shaba's talk, these features persist. The question is then becomes, is there a deconfining phase transition as the Gaugino mass becomes large compared to the QCD scale? And I note that yesterday Hitoshi was rather cautious about making any claims of this sort, but I want to sort of explore this possibility. Okay, so I'll first address the analogous problem in CPN theories in 2 dimensions at large n. Okay, and we'll see that there is a phase transition as one passes from the supersymmetric theory, which in that case is non-confining, to the non-supersymmetric theory, which is confining. Confinement in this theory is a feature of the far infrared theory, as it will be in the 4-dimensional case. And the infrared theory is different in both limits up to some rescaling of lengths. This will be different in 4 dimensions. So the 4-dimensional story will be different, but this one is still interesting and still illustrates this possibility of a phase transition. Okay, so in 4 dimensions, the problem is more challenging. If we deform the now confining supersymmetric theory with a small self-breaking term, we expect that confinement will survive given the existence of a mass gap. Okay, so that's going to be important. So that's going to say something about what the far infrared theory looks like, okay, in the small m lambda limit, but in the far infrared theory, it's not clear sort of what the difference is between small and large m lambda. So that's sort of where the issue is. Okay, so I mentioned, as I said, Maruyama's talk and these authors have recently put forth arguments that if one considered theories with anomaly-mediated supersymmetry breaking, SUSY QCD has many of the features we expect from ordinary QCD. Okay, and that, as mentioned, this is also described in some work of my own. And we'll hear, and we have heard more about this at this meeting. And stimulated by this work, we'll ask whether it might be possible to rule out a phase transition to a deconfined theory as the soft breakings increase. Now, again, I think my title was a little bit of an overstatement. I'm not going to claim to be able to rule this out. I'm trying to sort of outline what are the issues that one confronts in trying to address this question. So, and to address this question, I'm going to focus not on monopole condensation, which is sort of the critical element of the Seiberg-Witten analysis, but on the heavy quark anti-quark potential. So I'm going to take as a given that that potential is linear in the supersymmetric theory, and argue that a deconfining transition is unlikely, and also then try and spell out what are some of the conditions under which a transition might occur.
Okay. Are you talking about starting with n=1 super-Young mills? And
yes.
So do we know that we have confinement in n=1?
Yes, yes, from deforming the n=2 theory.
Okay, but n=2 in Seiberg-Witten with small mass is confining.
Defined, but the deformed n=2 theory, the deformed to n=1 is confining.
Yes, but with small mass.
No, with small. With n=1, n=2 breaking mass to n=1.
Yes.
That mass can be large.
So you're saying that even in n=1 pure n=1 super means you can prove confinement.
Yes.
No phase transitions when you have supersymmetry. No mechanism.
Well,
you can write down the action, and you can use holomorphy and so on to establish that for large breaking of the n=2 to n=1. Okay. This may have been a topic in the 2000 for a large n=2 to n=1 that confinement persists, that the monopole condensate persists. All right, so as I say, I'm going to frame this way. So I'm going to discuss the heavy quark anti-quark potential and sort of argue that a deconfining transition appears unlikely. Okay, so appears unlikely is hardly, as I say, hardly a claim of a proof. Framed this way, confinement follows from assumptions about the theory in the far infrared. So we go out to large enough distances. We know some features of this theory. And in particular, as I said, this argument that for small m lambda confinement persists says that if I look at distances large n lambda, I can ask what does that theory look like, and what is the difference of that theory with small m lambda and large m lambda. Okay, so I'm going to give some simple arguments for confinement, but I'm also going to point out some loopholes and why this story is not complete. So sort of an outline. I'm going to talk first about confinement and supersymmetric gauge theories very briefly. I'll talk about the CPN models at large N, confinement, remind you how confinement occurs in the non-supersymmetric theory and not in the supersymmetric versions of the theory. And what happened, talk about a little bit what happens as you pass between them. Then I'll give an argument for confinement in four-dimensional gauge theories as one increases the soft breakings to obtain what I'll call real QCD. And I'll talk about, I should have said the loophole, I really know loopholes are plural. I will really only mention some of these other topics, but they're relevant. Large N, okay, I think is some support for this picture. Including light quarks should not be an issue, like not necessarily massless, but light quarks. And I'll give some conclusions. Okay, so just to remind you a little bit about confinement in supersymmetric gauge theories. Proving confinement in non-abelian gauge theories without supersymmetry remains one of the great challenges of theoretical physics. Okay. And what's remarkable is that with n equals 1 supersymmetry, one can establish confinement in a range of gauge theories in a variety of ways. And these include, and this gets to this question before, following Seiberg and Witten, one can prove confinement by exhibiting monopole condensation in theories with n equals 1 supersymmetry, which can be obtained by deformation of n equals 2 theories. And starting with SUN supersymmetric QCD with n minus 1 massive flavors, n minus 1 massless flavors, excuse me. One can compute the massless flavors, I'm sorry. One can compute the spectrum for small quark masses, and then using holomorphy, establish that the system is gapped when one gives the quarks large masses. Okay, so for example, in the SUN n equals 2 theory with the adjoint field, there are n points on the moduli space of vacuo where monopoles become massless. So in terms of an operator U, which is traced phi squared, phi is the adjoint of the SUN. This is equal to U naught, so I'm e to the 2 pi I over n. This is like these phases we saw this morning. And these states transform into one another under a Zn symmetry. Adding a large mass for the adjoint field, one finds n ground states corresponding to the n possible values of the Gaugino condensate. Expectation value of lambda is e to the 2 pi I over n times some constant. All right, so just again, just a reminder that one has this monopole condensation in one, which gives a rather complete picture of these theories. Okay, so I want to talk now a little bit about CPN. Okay, the theories, the non-supersymmetric CPN models at large n, in 2 dimensions are confining and gapped. And what is similar to QCD is that confinement is a problem of the far infrared. So the far infrared theory in that theory is just a pure. Yes.
Could you remind us what you mean by confinement in the CPN model?
Yes, so here I mean that, actually I'm about to say, so the low energy theory is a theory with just a pure U1 gauge theory. So if I have charged sources, it's provided they're not integer multiples of the fundamental charge, there's a linear potential between a heavy quark and edge. So that's what I mean by confinement here, and this is a point that Witten stressed. We're back in a lot of Witten today in the 1970s. That Witten stressed in this paper, and what is different, as I say, is that turning on supersymmetry breaking. Oops, sorry. Yeah, let me postpone that for just a moment. So it's natural, in fact, to focus on a Wilsonian action with cutoff lambda W well below the scale of the theory of lambda, the dynamically generated scale in this 2-dimensional theory. In 4 dimensions, we'll be interested in lambda QCD. Okay, and as I just said, the infrared theory is a pure U1 gauge theory. Okay, and so confinement is a feature of that theory. And it should be noted that, well, actually, I already said this, I think, yeah.
Can I ask a question about
Sure.
that? So if you really have a U1 gauge theory, how do I think about fractional charges? Charges should be quantized to be consistent. No?
I don't think,
I guess he means that the UN is non-compact.
yeah, I think, right,
The U1 is not.
the U1 is not.
But in any case, mechanism confinement and non-supersymmetric case is totally different in CPM. Because there are no strings in 2 dimensions, right?
Well, you mean, yeah, no, right. So I don't want to over stress this
Yeah.
analogy. What I do want to say is that again, it's this, there's some dynamics at some scale, which is of order, which in this case is this dynamically generated scale lambda, and QCD, it will be lambda QCD. Okay, and we're just, and something in the far infrared is responsible for confinement. So the sort of thing I have in mind, I don't. You know, if we think about, say, Feynman diagrams for some quark anti-quark potential, or this could be some charge, some charge field in the CPN model. Okay, there are some complicated Feynman diagrams. And we're interested in both cases in whatever is the behavior of the system at very large distances. Okay, so in particular, again, just to stress this point, if in the case of 4 dimensions, where the theory is confining for m lambda greater than 0, okay, I don't know for how large. Question mark there. Okay. Then the spirit of this is going to be that the same set of diagrams, okay, with small or large m lambda. And so to ask what that tells us. Okay. All right. Now, as demonstrated again in the CPN models, the supersymmetric theory is not confining. Okay, and in the language of this language of the far infrared theory, the issue there is that the far infrared theory is trivial. There are no, what Witten showed is there are no massless excitations. Okay, so the supersymmetric version of the theory in particular microscopically includes fermionic partners of the scalar fields. So I've called these Ni. These are the scalars. Okay, these are the fermions. Okay, I've introduced a supersymmetry breaking mass term here. Okay. And sigma and pi are some auxiliary fields as is this chi. And that.
No, but this model at large and solvable, and you can see that the phase transition is at m equal to 0.
Yes, absolutely.
It's enough to shift a little bit.
It's enough to shift a little bit.
And
Right.
that's it
Right.
forever.
And that's different than the 4-dimensional case. Okay, and that's one of the things that enforces the possibility that, well, first of all, that as I said, that because of the mass gap for small m lambda in 4 dimensions, confinement will persist. Okay, and one of the ways you can see that is doing things along the lines of the things we heard about this morning, okay, where you look at some effective theory and you ask, which includes the monopole fields, and ask, does the monopole condensation persist for small m lambda? Okay, and it does. Okay. So as I say here, for any and just getting to this point, for any non-zero fermion mass, the gauge boson propagator behaves at large distances like 1/k squared, a very small momentum transfer. Okay, so the theory confines. Okay, so the theory, even with a slight breaking of supersymmetry, confines. Okay, and it's sufficiently large separations of the heavy charge objects. One can consider a Wilsonian action with only a massless gauge field and the potential is limited. So now let me turn to 4 dimensions and just kind of give the essence of the argument. So to address confinement, rather than attacking the question of the fate of the magnetic monopole condensate at large m lambda, can study the heavy quark anti-quark potential at separation R. Okay? And for confinement, we study arbitrarily large R. Okay, so we can look at arbitrarily small energy scales. Okay. And in particular, we can take R much greater than 1/m lambda. So in this broken supersymmetric gauge theory without matter field, small m lambda, the potential is linear. Now, because confinement is a feature of the far infrared, it makes sense, as we said before, to consider a Wilsonian effective action, scale lambda W much less than lambda QCD, in which the Gaugino has been integrated out. Computation of this action is not a weak coupling problem. It's not clear what are the appropriate degrees of freedom, or what are the leading operators in this Lagrangian. But we could imagine, but I'm going to sort of imagine this sort of hypothetical action. So then consider this theory, this softly broken n equals 1 gauge theory without matter fields as a function first of x, which is m lambda over lambda QCD. Okay, I'm going to restrict myself here to theta equals 0 for simplicity. Okay, so for small values of x less than some x naught, we know that the low energy theory confines in this gap. Okay, confinement is a result of some dynamics at scales well below the mass gap. For CPN, the analog was the gauge field in the far infrared, which is responsible for confinement. Now, the pure gauge theory, which we've integrated out this Gauginos, is confining for some y, which is lambda W, this Wilsonian scale over lambda QCD, less than some y naught. Okay, well, y naught is less than what less than this x naught I defined before. Okay, and now, provided the theory flows smoothly from larger y to smaller, you would establish confinement. So if you can establish that the theory flows smoothly with y, okay, you've established confinement. Okay, and so our focus in the rest of these remarks will be on whether and how this might fail.
Like I just think extended logic, you're trying to find what are the options proving confinement.
Essentially. So I'm trying to argue that in some sense, in this picture, confinement is almost, I don't want to say obvious, but confinement seems a rather natural result of the understanding of the deforming theory. And what might fail in that? Is sort of the spirit of this. So in some sense, what I'm trying to argue is that what we've been handed is a picture in which confinement seems almost inevitable. And what might be turning that into a proof? So I sort of illustrated this with this kind of picture I do of Feynman diagrams on the board. So let me first of all just think of this in the language of perturbation theory. Okay, so imagining that the potential is, and here I think I'm invoking the spirit of Witten's 1970s papers as well. The potential is some kind of sum of Feynman diagrams somehow. Okay.
What if we know that's not the case? From this Heiberg-Witten solution, n equal 2 even is not
Right. Yeah.
is not defined at all by
Right. No, that's right. That's right. That's right. Okay. So still, let's suppose in some sense that there's a sense in which we can think of this potential as arising this way. Okay. This is say if you like a rather, as I said, most arguments I can give are rather naive. If you think in terms of Feynman diagrams, okay, why, if you like, with the Feynman diagrams? Well, there are diagrams which involve, in this case, massless gluons, which are enhanced by logarithms. So there's a sum of diagrams with hours of logs of this distance divided by some QCD scale, this scale lambda W, okay, that I've defined. Okay. And these logs only arise from the diagrams with the massless fields. Okay, so the massive Gaugino, even the slightly small mass Gaugino, where distance is large compared to the Gaugino Compton wavelength. Okay, only the massless diagrams contribute. Only give these large logs, and so there's a sense in which there's something universal that the result then doesn't depend. Form of the result doesn't depend on the value of m lambda. Okay, so in fact, so the coefficient of the linear term and the potential depends only on sort of what is the effective scale parameter of the theory, which I've written here in terms of this G, some coupling at lambda W and some coupling at m
But
lambda.
if you are interested in at Q much less than lambda W, the coupling constant, I mean expansion and the coupling constant, it looks crazy, right?
Right, oh, absolutely, absolutely. So this is a statement about, so there's no proof here. This is a statement about sort of, if you just looked at the perturbation theory order by order and pretended that was a sensible thing to do, okay, you would say that doesn't depend on the value of m lambda except through this sort of QCD scale. I'll comment. I mean, these, as I said at the beginning, these may not be these are probably not the appropriate degrees of freedom to think about. This is there's some kind of effective theory at large scales. I don't know what that looks like. Okay, and so as I said, there's not a proof here. Okay, but in this picture, confinement survives at large n lambda. And this, in response to that question, I could be one certainly question the reliability of the guidance provided by Feynman diagrams. And I'm using the word guidance much, certainly not using the word computation. But one might hope that other non-perturbative effects, such as instantine, which are also dominated by large distances, large distances by the purely gluonic contributions. Okay. So, and the usual large N picture assumes that features of QCD are reflected in the planar Feynman diagram expansion. And as I try to say, this argument, formally order by order, is correct in perturbation theory. Okay, operators of dimension higher than 4 in the Wilsonian action don't contribute to all. So one could frame this other ways, which are really roughly equivalent and have the same weaknesses. Okay. We can assume, for example, we're going to frame this in terms of this Wilsonian action. We can assume that at large distances, there is such an action. It could be written in terms of gauge fields. Again, this is a statement which we don't really know hold beyond perturbation theory. It's plausible, and at least at large N is sort of usually we take to be an underlying feature. Okay, that within this the operators have roughly their naive dimension. In particular, there's a single most relevant or nearly marginal operator at U squared. Okay, an associated scale lambda QCD. Okay, and the computations of less relevant operators to the potential at large distances are suppressed by powers of R lambda W or even more R lambda QCD inverse. Okay, and I also have to assume that there are no zeros of the beta function for the leading operator. And it's possible to constrain that possibility. And again, if these assumptions are correct, the theory in the far infrared has only the parameter lambda twiddle QCD, find it here. And again, they're assuming the dominant coupling is the F squared coupling. All right, so we know the confinement occurs for small m lambda, and in this case, confinement depends only on the length scale lambda, tilde lambda QCD. Okay, and so that may change as we increase m lambda, but confinement with these assumptions occurs. Okay, so how might this fail? Okay, well, for in particular, integrating out the Gaugino with mass m lambda might yield effective theories whose behavior changes at some critical value of m lambda. Okay, and it may be possible to rule out some of these possibilities. This, if one could, this would perhaps be the basis of some sort of proof. So, for example, one possibility, which is a realization of the idea that there is could be a phase transition, is there are two distinct infrared theories with different degrees of freedom in the far infrared. one confining and one not. Okay, and above some critical value of m lambda, the theory matches onto the non-confining theory, and below that critical value, the theory is confining, matches onto the confining theory. And one can model this, okay, in analogy with the CPN theories. One can think of this in terms of some critical value for the monopole condensate, for example, okay, as a function of m lambda. Okay, you can imagine that there is more than one most relevant operator, perhaps with the same dimensions. Okay, the small m lambda theory might match onto one. Okay, in the confining space, subspace of that theory, and of those parameters, and the large m lambda to the other non-confining subspace. And this is very similar to the previous possibility. Okay, and you can also consider exotic possibilities, like there are multiple renormalization group fixed points. Okay, and effectively, again, there will be several different theories. Okay, and okay, this would have various weird features. Ordinary QCD would exhibit an IR fixed point. Okay, so there are various ways this might fail. I skip this, so there are various ways this might fail. All of them are rather exotic. The theory would have to go to some length to avoid confining as you added this in group and allowed this deformation to grow. Okay, so I'm going to conclude then. So even with large soft breakings, SUSY QCD is likely confining. Okay, so from these rather simple and, as I said, sort of naive considerations, it appears that by deforming supersymmetric QCD with large Gaugino and squark masses, one obtains a theory which is gapped and confined. And to summarize the basic arguments, first, the linear confining potential of the supersymmetric theories likely survives with small soft breakings due to the presence of the mass gap. The linear confining theory of the slightly broken supersymmetric theories can be computed at arbitrarily large distance. Okay, and for small lambda W and large R, only the Gaugino fields contribute to the potential. So one can work with a Wilsonian action with scale lambda W small compared to the soft breaking, but large compared to 1/R. And provided that there is a common set of degrees of freedom and a unique most relevant operator in this theory, the potential depends only on a single parameter tilde lambda QCD. And confinement in the small m lambda theory establishes in that with these assumptions, confinement generally. Okay, and increasing m lambda just results in rescaling lengths. Okay, so as I said, the last 2 points, and this gets to Isha's question, are basic features of the perturbative expansion. Okay, whose reliability is certainly questionable here. They might fail if there are distinct theories in the infrared, or if there are additional most relevant marginal operators at some value of Gaugino mass. Okay, this would realize this possibility of a phase transition. Okay, these arguments receive some support from large N considerations, and they can be readily extended to include quarks with small non-zero mass. Okay, so I'll conclude there.
I wonder, that, because when you showed the confinement in n equal 1, it's based on this kind of condensation of monopoles, right? However, it doesn't look like this type of confinement is the one which we expected in QCD, right? So, I mean, like a spectrum would be different, whatever, reflecting this particular abelian nature of this confinement. So it doesn't prevent you. I mean, it doesn't make it some difficulty for this.
Well, I think it is not. I think it does establish. I have to think about this question because I thought about this before. But I think it does establish that there's a linear potential between charged objects, and that's all I'm using.
No, I agree. Yeah, but then if we are trying then go to what kind of strings would be there.
Oh yeah, no,
you see the
absolutely. So all I'm grabbing onto here is the linear potential between.
I was just, one thing that, Moriyama told us about is that in some cases, I don't remember exactly which case, the kind of soft breaking with anomaly mediated supersymmetry breaking led to, a global minimum, which was not the one that looks like, QCD, right? There was a local minimum that looked like QCD, and there's a global minimum, which is
These are the forks, right?
yeah. And I would just,
So largely I'm focused on the theory with that.
let me just point out that in that case, we are relying on a phase transition occurring for that to give the correct picture, right? We are relying on them exchanging dominance.
Fair enough. I have to think about that. That's a good point.
A comment about 3D. 3D is more controlled and pure Yang mills in 3D
Three
confined
is 2 + 1.
without SUSY, pure
2 + 1.
2 + 1. So pure Yang mills confines. Now there is a very nice work of Sokomogotsky with Nati Seiberg in which they added to the SUN one adjoint fermion. And this theory, although it's an adjoint fermion, does not confine. So it's kind of life is or QCD is kind of full of surprises. How come SUN with one adjoint fermion does not confine? So and that's similar to.
I think that's similar to what I said about CPN, and I kind of hit a concern there. So I started out by saying, well, if there's a mass gap, expect confinement to persist. So what happens for the CPN?
Yeah.
Because the CPN is clearly a little different, and the level at which I understand that is to think really about sort of what kind of effective action I write. For example, for getting to the monopole story. Okay.
You don't even need supersymmetry in CPM. All you need
Well, absolutely not.
confinement is to add some number or at least one master score. That's enough.
Yeah, absolutely.
That's enough because if you add master score, then
Yeah,
the
absolutely.
effective photon,
Yeah.
which it realizes interaction,
Right.
immediately acquires a mass, and instead of the Coulomb growth and
Right,
you call
plus
it.
one
Absolutely,
dimension, it's exponentially cut off. So in this case, supersymmetry has nothing to do with this smartest score.
Absolutely.
I think also in the paper of Clay, there is a transition n=2, not n=1. They did exactly the same exercise with n=2 SUSY, and it was deconfined at small masses and confined at large masses. And it's very similar to what you're discussing, that there is a phase transition.
Yeah, that's right. Yeah.
Okay, that's a good point.
I think it's very hard to make such statements. We have so many counterexamples.
But you see, the presence or absence of the phase transition is very hard to establish on
Yeah,
various examples because they are all individual, right? The outcome is it's decided on the case by case basis.
Yeah,
Right?
I think the comment is just that in some cases, when you do soft supersymmetry breaking, you end up with a vacuum that looks like the one you want for the non-supersymmetric theory as a local, not global minimum.
Yes.
And so if that is a reliable method for discovering physics about the non-supersymmetric theory, you're relying on a phase transition, right?
Of course.
So since we have so many examples of that, it's very hard to imagine that you could make a general argument that there could be no phase transition.
I think we have to move on as we're pushed right at the edge of time, but let's thank Michael again.
It actually practice and great.
Did you open your file already?
Yeah, it's not.
It's as if it's a different desktop.
It must be a different desktop. Let me try.
Maybe there's something.
Yeah, yeah.
Say play. If you just play.
The play isn't working, but it must be on a different.
It's only one desktop.
Let's try this one.
Oh, yeah, the calculation. Did it say desktop 4 when you did that? Yes, there might be 1, 2, and 3.
Okay, number 2. That's not 3.
Even like.
No review, but he did.
Do I have it being keynote? Oh, I can't do it with PDF.
Oh.
I need to play. Yeah. Okay. I just didn't realize.
Okay, so the next speaker is Emily Nardoni, and she's going to tell us about these perspectives on your studies.
All right. Okay. Okay. So anyways, thank you very much to the organizers for inviting me to speak at this really fantastic conference. So on the occasion of Supersymmetry's 50th approximate birthday, I wanted to talk about a program that I've been involved in where I think we've learned some new and interesting things about a class of strongly coupled 40n equals to 2, and also in some cases 40n equals to 1 superconformal field theories. And this is what I'm going to say is going to be based on some works with various collaborators that I've listed here. I have really fantastic collaborators. Okay, so the 40n equals to 2 superconformal field theories of Argyres-Douglas type are very special in the space of n equals to 2 quantum field theory, 40n equals to 2 quantum field theory. So let me explain what I mean by this class of theories. So the first such theory was found on at a singular point on the moduli space of a pure n equals to 2 pure n equals to 2 gauge theory in 4 dimensions. The first case was considered by Argyres and Douglas, hence the naming of the nomenclature of these theories, and at very special singular points where mutually non-local BPS states become light at once. So these are theories that are effective theories of mutually non-local particles. And since the first example, there were many subsequent examples. And these are theories that are really intrinsically strongly coupled. There's no parameter that I can dial to go to weak coupling. And so in this sense, they're quote unquote non-Lagrangian. So what I mean is there's no useful Lagrangian that describes the conformal point of these theories with manifest n equals to 2 supersymmetry. That's what I mean. And one of the unique or interesting features of these theories is that they possess relevant operators in their spectrum that have fractional scaling dimension. In particular, these are operators that parameterize their moduli space, their Coulomb branch. And so this is another one of the distinctive features of these theories. So when I say Argyres-Douglas theory, I'm going to refer to that as the general class of such theories with these sorts of properties. That's what I mean. And I'll just say to the theme of this conference, I think these sorts of interesting quantum field theories were maybe beyond the imagination of what physicists were thinking about 50 years ago. So the fact that we now not only think that they exist, but can use supersymmetry to make statements about their detailed properties, I think is really exciting, and also makes me hopeful for what we might be talking about in another 50 years at such a conference.
But besides kind of special value dimension, in Argyres-Douglas point, you have vacuum degeneracy, right? Because this vacuum mutually kind of inconsistent, both are present, and then the theory is not well defined, right? Because you're it would be like a quantum mechanic when you have degenerate background state, right?
So I think that you can convincingly argue that you indeed would flow to an interacting superconformal fixed point, despite this apparent.
Independent of degeneracy, right?
Yes. Thank you. Okay, so there are a zoo of theories of this type that you can construct in string theory. And for my purposes today, I'm going to focus on one class in this zoo. They come with various different names. The namings are all very confusing. This class that I'm going to focus on today we'll refer to as the DPG, superconformal field theories. So these are labeled by a positive integer p and a G equals ADE group. That's what these theories are labeled by. And so, for example, the DPSU2 type theories, these are the ones that are at the maximal singular point on the Coulomb branch of the pure SO2P super Yang-Mills series, as was discussed by these authors. You can see this from other perspectives as well. More generally, this class was first constructed in type 2B string theory by considering 2B string theory on a threefold hypersurface singularity, basically of ADE type, also with some P label describing the geometry first by these authors. And they also have a description in class S. And so I'm going to refer to this description throughout the talk. It'll be useful. So in class S, you get them by compactifying the 62,0 SCFTs of ADE type on a sphere to 4 dimensions in such a way as to get out these 40 n equals to 2 superconformal field theories. And in particular, I compactify on a sphere with, for these DPG theories, one regular puncture, which is of full or maximal type, meaning this is the type of puncture that will give me a G flavor symmetry in the 4D field theory, and one irregular puncture, which is labeled by this positive integer P. For those familiar, P is basically like the fractional part of the pole of the Higgs field in the associated Hitchin system. That's basically what P is. And so the fact of this irregular puncture from this sort of class S perspective is where these kind of interesting, particularly interesting properties of these DPG theories are coming from. And I should say, really just for simplicity on these slides, I'm talking about these DPG theories, but so for example, one thing I can do is connect them to other sorts of Argyres-Douglas type theories by doing things to this regular puncture. I could get other types of flavor symmetries as well out of this class. Okay, so I think as is usually the case in physics, whenever I have multiple ways of looking at a problem, I can make some progress, and it's really fruitful to compare different perspectives. And so I just told you that we've, for I guess maybe 10 years now, had this nice geometric engineering kind of picture of these this class of Argyres-Douglas type theories. And what I want to summarize in this talk are some different perspectives that have been especially explored in the last couple of years that I've been involved in. And so first of all, I'd like to highlight some of the properties of new holographic duals of these SCFTs. And so what some of the interesting properties of these holographic solutions are. On the one hand, And on the other hand, in the later part of my talk, I'd also like to mention some work proposing new Lagrangian type dualities of sort of n=1 versions of these Argyres-Douglas type theories, which can also give you an interesting perspective on some of their features. So that's what I want to tell you about in the next, I don't know, few minutes. Are there any questions before? Okay, so first let me summarize the holographic story. So what we did is we found ADS5 solutions of 11D supergravity and that are dual to, of course, 40n=2 superconformal field theories. And so these are solutions that are some work product of ADS5 times some 6-dimensional internal space in 11D supergravity, dual to these DP-SUN type Argyres-Douglas theories, as well as the generalization to other like regular types of regular puncture. But like I said, and for simplicity for the slides, I'm going to restrict to this DP-SUN case. And so these are the first really fully realized identified duals of these theories with irregular punctures in the geometry. And so it's interesting to ask how the different features come out. Of course, class S with just regular punctures has been known for quite a while, since the work of, well, especially Gaugino Maldacena.
Sorry, do they have a regime when they're just purely described by classical gravity, I mean at large n, or is it sort of intrinsically screened?
Good, so this is going to be in the realm of supergravity, and these are indeed going to be large n.
So large n is enough to, or is there some notion of a large tough coupling for these theories that you need for getting to a supergravity regime?
Large n is good.
What was the flavor symmetry of these theories?
So these theories have at least SUN flavor symmetry, and I'm actually, well, so for the holographic story, like you can consider solutions with really like any sort of lower flavor symmetry. So kind of like in the class S description, closing the regular puncture down. Yeah, these are theories with the DP-SUN theories have the SUN flavor symmetry at least.
So in the holographic theory, version of that theory, if we take the one with maximal flavor symmetry, we will have lots of gauge fields involved.
Indeed, indeed, that's right. Okay, so first, let me just summarize some of the checks that should convince you that we have a sensible picture. So this is a really brief summary. So for example, I can check that of course, the isometries of my ADS solutions reproduce the correct flavor symmetries that I'm trying to reproduce in these quantum field theories, in particular, including the SU2 times U1R symmetry of these theories as n=2 superconformal field theories. We can do a holographic computation of the central charge and check that it coincides with the large n limit of the central charge of these DP-SUN theories. I wrote it here for example at finite n. We can compute via some methods that I won't have time to tell you about the SUN flavor central charge and check that it matches again. And we can also check M2 brane probes wrapping 2 cycles in the geometry or in the internal space. And these are going to be, we can identify the configurations that are dual to Coulomb and Higgs branch operators in the SCFT, and we can correctly match, at least at large n, their dimensions. Yeah.
How does the GC part come about?
Good. So holography is a large n story, and the GCD will, here I wrote the answer for this like maximal SUN flavor symmetry. There are different expressions that depend on that for the different types of punctures. And kind of the statement is like, depending on the amount of flavor symmetry, you can correctly take the large n limit of what the GCD will be, and then you match it with the gravity. So gravity doesn't literally produce a GCD, but for all the different ranges of parameters, we get the right answer in the appropriate large N limit. Yeah, that's the statement.
I have another question. What geometry gives you SUN isometry for arbitrary large N?
What geometry gives you SUN?
So explicit branes, right? You probably have explicit branes.
It's not an isometry, it's a gauge fields.
So the SUN is going to come, I'll show you in a second. Ask FPBN if you don't understand it. Oh, was there a question?
It was the same question.
Okay. So let me I'm going to run through just some of the particular highlights of these holographic solutions. And so the first highlight is that they exhibit a somewhat novel means of preserving supersymmetry in 4 dimensions. And so let me explain this. So the internal space of these solutions consists of the S4, which is transverse to my M5 brane stack. Remember, I'm describing theories that are like N M5 branes wrapped on like in this like geometric engineering picture, like this sphere. And so I have this S4 transverse to the stack times a 2D space, call it sigma. And we're trying to preserve N equals 2 supersymmetry. So this S4 decomposes into a circle direction, which is dual to the would-be U1R symmetry of the field theory, and an S2 direction, which is dual to the SU2R symmetry of the field theory. It's an interval. And this 2D space sigma, this is topologically a disk. So I'm kind of drawing it here with an orbifold singularity at the center of the disk, the SUN flavor symmetry is coming from exactly this part of the geometry. There's a monopole source of charge N at this part of the geometry.
So it's like form fields wrapping convention to some.
Exactly. So I can think of exactly. And so it's this topological disk, which is the thing in these solutions, which is dual to this punctured sphere, and interesting. And so, like I said, at one end I have this orbifold singularity, and at the other, or in the center of the disk, and the disk has a boundary, and on this boundary, there's a U1 gauge field that has holonomy, which depends on these integers P and N. Interestingly, these the killing spinors are not constant on this disk; they vary in this direction, and so this is preserving supersymmetry in a way that is not the standard topological twist. So that's one of the interesting features. And I should also say, so maybe some of you are familiar with the spindle type solutions that have been discussed recently in various contexts in supergravity or in holography. And you should think of this solution as basically like a half spindle. That the spindle is topologically, it's an S2 with conical defects at each of the poles. Here, this is kind of like cutting that in half and putting some holonomy at the boundary. Okay, so I said that this space is dual to this sphere with a regular and irregular puncture, and so precisely this, as I said, this part of the disk with the charge and monopole. This is the thing that's dual to the regular puncture. And that contributes to SUN flavor symmetry. And this you can get by really locally identifying this geometry with the one described back by like Gaugino and Maldacena. They understood these regular puncture type geometries a long time ago. Now, interestingly, on this side of the disk, I actually have a singularity of my metric. And what we're able to do is identify this as actually M5 brane sources, so internal M5 brane sources, which are extended on the ADS5 directions, as well as this circle direction of the disk, and smeared over 2 of the other internal directions in this space. So that this is the part of the geometry that's dual to this irregular puncture, and that's where like this integer P is coming in.
Is the curvature in the orange region small?
Is the curvature in the orange region small? Let me think.
You said this is geometric singularity, right? So
Yes.
does that mean the curvature is big?
So it means that the curvature is big, but what we do is we zoom in, but like we can, but what we identify like the right-hand side of the equation is exactly like the M5 branes located at that spot, like on the boundary. Does that make sense? So like it's a singularity, but it's a singularity of like the supergravity that you should interpret as M5 brane sources. That's what I'm trying to say. But indeed, this is weird. So like these, I mean, we did a lot of convincing to convince ourselves that like these.
And the killing spinner and is it topologically twisted as you go towards the blue region? Becomes constant in the blue region somehow?
Good. So it goes to a constant value at the blue region,
So
but it varies across W.
It does match on to the Gaugino-Maldacena.
Yes, it does exactly match onto the Gaugino-Maldacena solution in the blue region. Yes. Okay, and the last feature I just want to point out of these solutions is that, well, in the Argyres-Douglas type theories, one of the unique features is that the R symmetry, the superconformal R symmetry, mixes the would-be U1R symmetry with the global isometry of the sphere. And this is manifest in this dual description where you can check that the isometry dual to the superconformal R symmetry mixes this other circle direction transverse to the stack with the one of the disk directions with this particular ratio that depends on the integers in exactly the right way. Okay, that was just some lightning, like I wanted to point out some of the interesting features of these solutions. They're relatively recent and they immediately lead to, I think, some open and interesting questions. So, okay, obviously we should try to realize other classes of Argyres-Douglas theories holographically. That should be doable now that we understand the main ingredients. It would also be very interesting to study holographic renormalization group flows among these different theories. So for example, they have n equals to 2 preserving deformations, n equals to 1 preserving deformations. Now that we have these holographic solutions, it'd be interesting to study the holographic versions of these flows. It would be very interesting to understand the classification of irregular punctures from the holographic side. This is actually really non-trivial because I didn't say this, but the way that you relate this integer p with the natural flux parameter that appears in the supergravity solution is very non-trivial. And so I think it would take some thinking about how to do this sort of classification in a general way. And I think it could be very illuminating. And further, I want to just mention that I think that we should take these dual solutions as inspiration for thinking about new classes of strongly coupled n equals to 1 superconformal field theories. So the kind of basic picture I have in my mind is that now we have these building blocks that are like, they're like these half spindle building blocks. So it's like these irregular punctured spheres, the duals of the irregular punctured spheres. And normally in class S, I don't know how to glue these spheres with the irregular puncture. That seems impossible, or no, we don't know how to do that in any sensible way. But with this picture, you kind of have this like very naive idea that I should be able to do this at the level of these half spindle solutions to get these actual spindle solutions that we know exist and should correspond to n equals to 1 superconformal field theories. So is there some analog of this picture in the field theory? Can we understand some kind of new geometric building block? I think that's an interesting direction. Okay, so in the last part of this talk, I think I have 10.
A little bit less.
Okay.
7 more.
Okay, perfect. I'd like to mention some other set of dualities that I've been thinking about involving these Argyres-Douglas type theories. And these are dualities between the Argyres-Douglas theory on one side and or some deformed version of it on one side, and a purely Lagrangian field theory on the other side. And when I have such a duality, that's very interesting because there are things that are easy to compute with Lagrangians that are very difficult to compute in these strongly coupled fixed points. And so for this remainder of the talk, when I say duality, to be really clear, I mean in the sense of the same universality class. So I'm talking about two field theories that maybe look very different in flow, and we're claiming flow at low energies to the same superconformal fixed point. So I told you, what do I mean by a Lagrangian dual? So I told you there's no Lagrangian for these strongly coupled field theories. And indeed, there's no manifestly n equals to 2 Lagrangian. But in some cases, dual n equals to 1 Lagrangian quiver renormalization group flows have been understood. So basically, there have been situations where on one side I have this Argyres-Douglas type theory, and on the other side I have some n equals to 1 quiver gauge theory, which I deform in a certain way, and is argued to exhibit enhancement of supersymmetry to n equals to 2 at low energies and flow to the Argyres-Douglas fixed point in some cases. Some of these cases include the holographic solutions I was describing before, so there's some overlap between these sorts of Lagrangian duals and the holographic, and the cases where we now know the holographic dualities. And so this is very interesting when I know it. I can compute things like the superconformal index. I can get insights into the Higgs branch of the Argyres-Douglas theory, etc. When I have such a duality, and we in fact use some of these duality checks as checks of our holographic solutions, but when these like Lagrangian duals were known. And so just in the last couple of minutes, I'd like to describe some new example of Lagrangian duality for an n equals to 1 version of one of these Argyres-Douglas superconformal field theories. So some n equals to 1 deformation of one of these that's still strongly coupled. And the spirit of this idea comes from thinking about these strongly coupled superconformal field theories as generalized matter building blocks. So we all know very well in Lagrangian field theory how to build gauge theories by coupling free fields together. So for example, one thing I can do is I can gauge a global symmetry by coupling vector fields to the current in the Lagrangian. I'm doing some like pictorial notation where gauging a global symmetry means changing like a box node to a circle node. Or I can gauge diagonal subgroups of global symmetries, thereby gluing together different sorts of building blocks. And the claim is that it's more generally interesting to consider interacting superconformal field theories, even strongly coupled ones, as these sort of generalized matter building blocks, where say my superconformal sector has some flavor symmetry. I can still do something like gauge the flavor symmetry, where if I'm in a supersymmetric case, I mean couple n equals to 1 or n equals to 2 vector multiplet to the current multiplet for the global symmetry. And the statement is that by doing these sorts of gauging operations, I can build more general, possibly quote unquote non-Lagrangian field theories, and sometimes even compute their IR properties using supersymmetry. And so this is kind of like the motivating idea. And it's an idea that's very familiar from class S. So for example, in class S, these sorts of gauging and gluing operations are known very well to geometrically correspond with, say, a pair of Pants decompositions of the Riemann surface. Okay, now let me tell you what I'm going to, the proposal I have today. So let's start with some DP-SUN type theory. It has, like I said, an SUN flavor symmetry. And for this last part of the talk, restrict the GCD of P and N to 1. So these, let's take these to be co-prime integers. This just means that the flavor symmetry is only SUN, and it simplifies all of the formulas and makes everything closed form so that we can work with it. Now, first, I'm going to deform this to an n equals to 1 theory by adding a superpotential And the superpotential is going to involve the Coulomb branch operator of smallest dimension in my DPSUN theory. And kind of the tagline of when I do this deformation is that this makes this n=1 deformed DPG type theory into a G adjoint chiral multiplet, morally speaking. It behaves like a G adjoint chiral multiplet. So it flows to a CFT with the same Toft anomalies and a Schur limit of the index as an adjoint chiral multiplet of the SUN symmetry. And this is like really precise for the case p=2, where it's been known for some time that this really just flows to like n² - 1 free chiral multiplets.
Sorry, Emily, what is delta in that last line?
Good. So I mean that like this thing behaves like an adjoint chiral multiplet with dimension, this fractional dimension that depends on p. So like its Toft anomalies, etc., look like if I plug in this fractional dimension.
Okay, you're not saying that there's a real such.
No.
Okay.
But I'm saying that like it flows. It's some strongly interacting thing, but it has some of the characteristics. That's what I mean. But this is an inspiring observation, so we're going to use it. And so first, second step is we're going to. Okay, great. I'm almost done. The second step is we're going to couple this theory to basically SUN SCFTs with NF fundamental chiral multiplets and anti-chiral multiplets. And then the claim is that this strongly coupled n=1 theory, this thing I just constructed, is dual to 40 n=1 SUN adjoint SQCD with an adjoint chiral superfield and a particular superpotential, which is this trace x to the p+1. So I'll remind you that the interacting fixed points of this n=1 SUN SQCD are classified by their superpotential, and the forms of the possible superpotentials are exactly these powers of the adjoint field, and that for of course p=1, this is just a mass term for the adjoint chiral, and so this is just plain old SQCD, which we know participates in Seiberg duality with a dual SU-NF-N gauge group. And the p greater than 1 cases, so cubic or larger superpotentials, also have Seiberg-like duals with SU-PNF-N gauge group that were discussed by Kudasov and Schwimmer. And so the statement here is that there's a conformal window in which these SCFTs have yet another dual description in terms of these Argyres-Douglas type theories. And maybe for lack of time, I won't go through some of the checks, but feel free to ask me later. And I'll just end by stating some of the, I think, interesting open problems. So at present, this sort of duality proposal is most interesting for actually learning about the non-Lagrangian theory. So like if I know things about the Lagrangian dual, then I can learn things about, for example, the chiral ring of operators, like quantum ring, possible quantum ring truncations in the dual. I can maybe use it to bootstrap the full superconformal index of these strongly coupled Argyres-Douglas theories, etc. And so one should try to do that. But I think it would be very exciting to turn the logic in reverse and to extend this idea of this one adjoint duality to a two adjoint duality. So this would be a duality that involves two of these DPG type building blocks. And doing so would be really interesting because the two adjoint theories in SQCD have some lingering puzzles with their proposed Seiberg-like dualities. And if there's some way to address this in the context of a completely different dual description of these theories, I think that would be extremely interesting. It's still a little bit of a dream right now, but I think it would be very interesting. And then finally, I just want to comment that like I emphasized, these DPSUN theories now have these holographic dual descriptions, and so we should try to use them to understand the duals of their deformations, including these sorts of n=1 deformations. So just to conclude, I told you about some of the recent work on different dualities of these n equals to 2 and their n equals to 1 deformations, Argyres-Douglas type theories. And I just want to emphasize that I think we really have the most to learn by thinking about the intersection of these different perspectives, and that could really be the most informative approach to making progress in the future. So with that, I'll end. Thank you.
Questions.
No, I think to return back to that I was asking before, that now my understanding of this Argyres-Douglas point is that you have kind of mutually non-local description, right? And I would be thinking about, like having some physical objects, different kind, which are realizing this kind of non-locality in description, right? So you can have kind of, I don't know, starting from one side, you can have kind of I don't know, some kind of excitation which would remind you of existence of the other phases. And it's different than just I mean an anomalous dimension, right? Because anomalous dimension operator you still could continue to consider the superconformal point, it's okay, but it doesn't realize this idea of kind of mutually non-local object in the theory near this point. I just that's one.
Thanks for the comment.
That is algebraic for three-dimensional theories, like form.
Good. So we haven't considered the reduction of these to 3 dimensions, but one could ask about that.
Like, does the holographic dictionary that exists, or like it is 4 times something?
Well, so here I've only talked about the ADS5 case, and that's where we've done. So I don't know if I go down to 1 dimension. I don't know what would happen to these solutions if I go down 1.
Because in 3 dimensions, there are also this interesting facts when they have different UV descriptions and both the same IR fixed point. Similar to what you said about engaging.
Thanks.
So when you had this slide where you had basically the adjoint being the confinement to this DP theory, potential. So this is, I mean, it's not like you are saying that you go to some point in the conformal manifold. So it's like an infrared statement.
It's an infrared statement.
Because it's n=1.
Yes, it's an infrared statement. Yeah.
And so what are the evidences that you have again? It's like checking the index basically to see that it's the same, describing the theory with the adjoint or.
Yeah. So like, okay, central charges, Tift anomalies, index, matching of chiral operators. One interesting thing is that the truncation of the Masonic operators on either side of the duality. So this is known, of course, in adjoint SQCD description, but follows from like a Higgs branch, a non-trivial Higgs branch relation in the DPG type description. So so it passes like the first set of basic tests.
But it didn't have the superpotential that leads to from 1 to 4. So there were similar statements made by in the sense of a conformal point.
Oh, good. So good. So it's very important in this story that we add a particular superpotential, and adjoint SQCD without its superpotential doesn't have any known duals, but is still thought to flow to an interacting superconformal fixed point. And we don't claim that we can find the dual of that fixed point. So like our theory without the superpotential, we don't doesn't flow to the dual of that fixed point. That would be extremely interesting because we don't know a dual for that fixed point, but we're not claiming that. We're making an IR statement about the theory after I've deformed with the superpotential. But yeah, thanks.
So do you understand the Schwimmer duality in a geometric theory?
So it depends what you mean. So we know Kutasov-Schwimmer duality from we understand that very well in the field theory context. And so now I'm claiming we have this other dual description of the same fixed point. And so all of the sorts of checks I would do for one side hold for the other side. I haven't used this proposed duality to make new insights about the magnetic dual, but
this tells you something about gauging this Argyres-Douglas theory. So two different gauging systems, different theories should be the same.
right, yeah. So
So that, do you think there will be a class SH understanding where it is?
maybe, yeah, maybe. I think it's interesting to think about.
Oh.
I have just the illustration, the different pieces here, and Douglas is mutually.
That's good. Indeed, yeah. We can't write a Lagrangian that describes the No, I think
But it's wasn't me from the very beginning. But
So easy for
No. I was suggesting that. Look, you are mutually involved in this practice. It's clear, right?
I think we've moved into different selection sectors. I'm not sure that we're mutually involved.
You are here. He's not. He's back.
Sometimes.
Now where? I mean, because he was moving around.
Well, I think he's mostly working in this financial stuff, but he still writes these papers, which I don't know if you guys have read these ones on kind of computability, high level notions of constructability or computability.
I see, and so more generic. No, it's example.
So I just sent you those old references that I mentioned. I suspect there are subset of the geometry is reflected.
excellent. Yeah. I'll take a close look.
I think it's fair to start.
Remember, I did ask you what was
What do you mean they end up?
Let's start from spindle. And find the which order theories the result of 60 on the spindle.
Exactly, they should be 40 and equals 1
But
theories.
it's really what happens if the supergravity solution is the metric poles and the solutions are actually spindle.
Okay, I would be extremely interested to see why you see that, because I've studied, there's like one paper that's done this, or even started looking at this, right? And they like barely did like anything, and so like they haven't so they wrote down some basic facts about this, like the reported like 40 and equals 1. Well, yeah. There's this one like smart like
They all
that
start
I've
out kind
written
of
on a single paper.
Some of
And
them
so
are-
like those solutions I've been needing to look at more closely.
So I
Still doing the same question here.
Have we found that they're split into two?
I see. So you
So
think
they-
they're unstable?
No,
Like,
so
what
I
do you
think
mean by-
what it means is that these counters are actually.
We've been writing down symmetry.
I see.
So it actually break up into.
Yes, then it'll
different
two
sectors.
decoupled
And I think it's close-ish.
But like,
Closest to being done from the
but
beginning.
do you think that there's actually stable and equals to 1
So,
point?
So you start from
working
negative
about
1.
this. Thinking of this, like,
Yeah.
eight
Because
months.
it's just
We're
like
making,
fucking 560 units.
I think we should use it as well.
And then you do the little bracket thing. And it seems to it's one of.
And there is a laser swing on
I
that as
really
well.
been using it in this line, or is this? really
So maybe what it says suggests that the insurance is.
Yeah, that's
I mean, it's some work.
So you can press the middle. that'll be your laser.
Yeah, you
But
press
just
that.
finding your top
Yeah.
one.
Yes, we also do have.
That's extreme, yeah, that's.
Green laser pointer if you want that, or the stick so you can hit it.
Yeah, but also there's also was the test found at some point.
Oh, is that true? Because, yeah, nothing like that is appeared in the literature.
Two is.
I've heard this declared as the first one protocol.
Maybe. Pretty cool, right?
You ever tell them that it's only to apply the.
It's like, it's
Yeah, so,
pencil,
so
it's like,
it's just a
okay, you
chapter
should be able to get this
when
one
I
like
took
two
one
keys,
from Cherman,
like the right.
One
pencil,
understood
but like the
chemistry,
most
chapter
obvious, yes,
4.3.
doesn't work. Like the problem is like the mixing.
So,
of
you
the
know,
two
I,
guidelines.
with my
So,
students, I agree, it's too much.
I still think. you could
Beginning,
do
I tried to,
something, but
although
the
it's
most obvious
hard, I
guesses
tried to
don't
actually
work.
make them for their first project, do it by
Yeah,
themselves.
that got me all excited.
Because I wanted to like sometimes not work. So like if I just group them with like in a group, I won't be able to distinguish.
No.
Right.
Yeah.
Later, it's okay if they're all in the group already together, but at the beginning, like they gotta, you know, I mean, it's good to train to like write the paper on their own. Understand what is the threshold. for when something is. This I discovered is something. I think it's because like when I was a postdoc.
So,
And for
okay,
myself, this was
so there's
like
one exact
intuitively
statement, which is that
obvious.
the
when the
DPG
project's
theory
done.
defines
Yeah,
the
when the project's done, but
does
also
flow
like,
to free chiral.
like, what's the difference between a note?
With P equals 2. Okay,
Right?
so like,
What's a,
for
you know,
like the.
what's like a correct argument
the
that I can show
first
to you in a public forum, and what's just like some garbage. that
Case
you
of
show
like the
each other.
DPG theory
Right.
is like, you know, it's all
And,
free,
you know,
like you
I-
can check that this really just flows to
When
free
I was a
chiral
postdoc, I
splits, and then
only
your
worked
intuition
with
is really.
students who are, you know.
Beyond that,
so
it's kind of
their
just like
advisors can't give them
intuition.
enough work.
So
I also
like,
never have to teach it.
like you should, it kind of behaves like an adjoint chiral, but you need to do
That's
more
not-
check, like you
that's
can't just
something that's
replace
natural.
adjoint. So you might start replacing things like adjoint chirals with these like blocks, but then like you have to do more checks to make sure that you're actually doing something sensible and not, you know. It's not a literal.
I do,
Yes, the
The
recent.
conjecture something going down.
I talk a lot
Yes,
to
they have
Son and Levin
Yeah.
and to Jeff Harvey.
Yeah, that's right. So they're like, yeah,
Uh,
yeah. So yeah, that's the one that just came out, right?
And Mark-
Yeah, so I still need to read it in detail.
So presumably can you
So,
deform by
kind of less
potential.
plugged into.
There is construction, you should let the state.
You should, yeah, exactly, like,
There's something
because
around, but somehow.
this should live in the same universe. But like, yeah, you should be able to take their stuff and then deform with this sort of,
Their own
super- or
stuff.
like even other
Yeah,
super
they're right.
potentials, try to do more interesting things.
Somehow
and,
not that react.
Yeah, exactly. Yes.
IR state.
I mean, actually, I think this started when I think that I caused it to start
Yeah.
because I just like declared, like, I will eat lunch every day. in This giant picture, like right next to
Then
my
you can go
office.
and check.
It's fine.
Why you expect that.
That was somehow enough.
I see, yeah, yeah,
Started joining, yeah.
I see.
Yeah, it's been a couple years, 3 years. It's my end of my 4 years. My God, we're getting old.
So it doesn't suggest that it's only when you have this versus that. Yeah. The same amount.
It's great. It's too bad we don't have people here.
Yeah,
What? What was
Yeah.
that?
Yeah. And there's some
Can you
non-trivial
say that
A
again?
maximization that happens, right? Like, I mean, all these theories involve A maximization.
But I don't know, it might be the kind of place where they want to.
It was kind of just like a fun observation, but I think it's.
Go through the motions.
Yes. Well, I mean, it's ironic.
Yeah.
I don't think. They kind of incentivize you to get other jobs.
It is.
Yeah, they do.
Well, I mean,
Yeah.
yeah,
It's a weird thing.
my favorite is Brody.
Yeah, they're like,
So I am interested in possible.
Exactly.
No,
I don't, like, I don't know if it'll work out for like. maybe it's a little bit of type three, but
Yeah, I know. I intentionally
They
disconnected.
consider CPU.
Just now, yes.
And they.
Oh, no, and then,
She fixed this. She fixed it.
exactly.
Oh, I see.
That was the object.
To themselves, that they make an exercise in terms of the.
Yeah, exactly, like, you know, like, you make this statement at the beginning of these sorts of talks, you know, this is my relevant operator, for example, like, I do it as like fractals, that was mentioned. I mean, it's n equals 1, it's different, but like still, like, that's exactly the observation. here, is
I
that
was going
that's
to,
fractal.
basically, I thought I only had 2 papers with SUSY in them, but it turns out I have 3. I wanted to change 2 to 3. But they only have Acrobat on this computer, and to change a PDF, they want you to pay. So I'm like, I just wanted to like put a number in it. So there was one a couple of years ago, with a student, not with the 2 students. I wanted to know what the business of the battery cost. And then the other one was from many years ago.
You mean for my capability or?
They can't
for
fire.
the-
So
this is what. It looks like.
Resurfacing.
Erich formal windows.
Wow.
Some moderately.
It's not.
Like the.
Some point of view,
Maybe like.
That's
In-person education.
So if you rewrite it.
Okay, so you really have to
Like,
be
was
careful
was
to
that
check
even
like
in
that.
question?
What are the range? or, like,
No, that's
the
very scary.
load. And
Fine.
this is different in the Argyres-Douglas. This is actually an interesting part of the story. So you have the vacuum stability bound. Like SCFT theories, like
Yeah, I
there's
think
this
we'll face
bound
an issue.
on NF versus NC, that NF has to be bigger than NC over P, like
Not so.
power, so that there's a stable
Can't really
vacuum.
replace them.
So that's like an absolute lower bound.
In terms of this factor, this.
So actually, if you look at like the Argyres, and then like the actual lower bound of the conformal with magnetic, like Kudasov theory is higher than that.
Here, something like.
But if you look at like our Argyres-Douglas deformed theories, you kind of get like approximately the same, like the vacuum stability bound.
A is coefficient which is built in the second.
From like the existence of the fixed point without the superpotential.
Yeah.
So this flow from like the theory without the superpotential. When is
These two are
relevant because they were the question, and then when does the relevant operator like cause a flow? And like sort of like checking those things.
This is another notation for CPU. Generically.
So there's a range where it is, yeah, the claim is there's a range where it is, but you have to be really careful. I mean, of course, even if like you spectrum or duality, you have to be really careful about like the bounds of this. Like,
But you always have.
they actually probably an recommendation. So we have to do the same for like duality.
Yeah.
And see how it matches up.
Fortunately, it seems that it is.
That's very shocking, because then you'll.
Either plus one or minus one. This means
It's so good that you can't.
Yeah.
very much.
That's a very hard.
Because this is expression which close to zero. This here we can have effectively can be if you define your fields, that means instead of this here.
Yeah.
Those also see, some kind of people, and then those.
So it's more sphere, something like few components. Or melon, something like this. So the question is,
The thing with the power.
metaphysics in magnetic phenomena. Actually, this CP1 is, okay. One, so it is considered as a solid in magnetic field. This is Heisenberg description, okay, the standard, it's just this one.
So, sorry, so you demonstrated that there could be phase transitions. So this claim that when you break n equal to 2 n equal 1, there is it's not possible. There's no guarantee.
Have you not to n equals 1? We broke n equals 3
applications which must be, which could be
then,
extracted.
you know, no one will be
Placed
working at all. And so this puts a potential on the this course.
Yeah.
And there's a for small SUSY breaking parameter. There's
This is,
global
this
which is
is,
some deconfined string.
more so the length, basically, effectively, you can think of this.
And then there's a
change.
which is at the say monopole point.
It's a relative.
Monopoles are condensing, leaving.
Now, all this target space.
It's not the global minimum, so you know,
Doesn't-
so
Again,
if you think that this is a good picture for
It becomes a
finding confinement or finding the dynamics of non-SUSY theories, you are
So you
applying,
want a phase
you actually
transition.
want a phase transition.
Right, but that's breaking to n equals 0. His claim was the breaking to n equals 1.
For n equals 1, the claim is that, I think there's a claim that you cannot, you have a phase transition, but when he was talking about.
You cannot have a phase transition in specific quantities. But he's talking about confinement. The other parameter, the Fourier complement. The Fourier complement is not all quantity. So what protects the Fourier complement from acquiring the
what is separated this?
so I don't understand.
Usually you have a
Well-
lamp.
Yes, yeah.
It's
How
not a
about,
protected
but
quantity.
how about the, let's try something easier for a minute, which is, let's try to ask if the gap. So let's just ask him if it stay gap, if it could become gapless or.
But mass gap is a different issue.
It's a different issue, but.
Like in the example of SOAR, the theory is but probably there is a mass gap, but followed with a TQFT, right? That's what happened.
Like this side.
In the example that you have in 3D with the one agent Fermi, it's deconfined.
So you say
And
the standard
reason is that there is a
which can be
TQFT.
yeah. Now,
But they can solve a mass gap.
solid one, but you say, okay,
Yes.
because
But then there is also the spectrum is a mass. So mass gap and
Yes, there are separate things.
Right,
I
separate
think,
things.
I think, but maybe just
space,
first
it's
degree
splits
as a
into
function of the
two.
holomorphic parameter,
yes.
the gap can't, the gap will stay.
Okay.
We're discussing whether when you break.
Where do you use, whether
one,
it's
whether
The
there
guarantee is confined.
the guarantees confinement even for large.
How just
I can rule out first order phase.
no reason at that time.
In which quantity?
considering yes.
Holomorphic.
This is
But softness is all the parameter for
actually
polytopic, which is all the parameter. It's not holomorphic. It's not protected.
we constructed a similar model.
How it's not protected.
You are with my
How?
so I don't know now, but so this spherical one. Will be
I mean, it would imply that there would be one with, so. Such a case. Maybe. Let's see if we
Like
can
you
do
can
the
do
same thing.
the index, Witten's index. You compute the Witten's charge in presence of this, what is called the vortices. Whatever. This is close.
Twisted losses.
Yes. Yeah, yes. So you can rule that. However, if you charge the different, if there is the confinement.
So you are suggesting a different, a new criterion for confinement. You are trying to argue for confinement using this.
So, but
materials,
there are
right?
two complex.
You're talking about the generosity of.
You just, the generosity of backbone service.
Modify two is equal to, right? It's like two components of the reduction. Right?
Yes, yeah, but those.
Most likely there was a jump in the winter. You can rule it out.
Yes.
Something.
Like this? Yes.
You guys broke like a zero.
Yeah.
Then it's indeed, it's a.
They broke 20.0. One I feel you'll never get any phase transitions, not second order, not first order, not.
So you say this solid or.
Any complete designer which is story with then adding a mass in the mass to the adjoint, part of the adjoint to break many cases
To cut off here.
and then the kind of point of line is that
Supposed to like this.
confinement persists to any mass. Because there cannot be phase transitions.
Yeah.
So what I'm asking is. For non-homomorphic quantities. Result suggests something
It's not
else,
my
it
case,
says
but
the
expect-
Witten index.
Yeah, because Witten index doesn't jump. As a function of homomorphic parameters. It's like this.
This is.
But that relies on holomorphic. So if you have a non-holomorphic.
No, but the number of but what he's saying so is that
Yes.
just the number of factors.
Right, I'm happy with that. I thought Adi was asking about what happens if you just completely break supersymmetry.
No. Working from n equal to 1 to n equal to 2 to n equal to 1, okay, n equal to 1 pure superring mills.
Yes.
Which is obtained by taking the mass of the adjoint of n equal to infinity. Now, Witten index calculates SUSY factor.
This is the same as this or what?
This is target space. Here is.
And why on the target space there is this singularity?
Yeah, really.
The deconfined factor should jump from. I mean, the number of factors from 1 to n.
Yeah.
So it's not the same with this.
Okay, let's see.
Maybe you can, the chiral symmetry gives you an vacuum with confinement. Yeah. But maybe you could get n vacuum also. I mean, sorry. This n vacuum appear only after a certain.
Maybe it's the
Each single vacuum.
tip here has a very large.
You see what I mean?
Large
Vacuum.
this limit. So,
It's on the same.
but there are, in this case, there are two. Because there's plus, but there is.
Again, there's no deconfines, there's maybe chiral symmetry.
At the same point.
At the same point.
So you could imagine the n chiral
One or minus one, so
only one
this
vacuum.
thing is symmetric. So there are, if there is one tip here, then there should be another. So maybe that's.
Because the chiral condensate, the homomorphic function.
Nice. That does.
So you cannot, you cannot make it vanish.
Good, that's continuous. The chiral condensate, the Gaugino condensate is protected.
Yeah, so you can rule out this entire.
Yes.
So
yes,
I
agree,
feel
I
you.
agree. The Gaugino condensate is protected. No,
Yeah.
about that. But then, if he's then kind of make it a solid argument, it has to be like.
And what are, I mean.
You have to find some, let's say.
Consider any
more
applications of this or. What
What
for?
to super symmetrize it somehow into, you should have a direct.
No,
quantity, which is an order bound of confinement, which is all.
But if
You have to.
you agree that as a function of homomorphic parameters, there's no phase transition of any kind in.
Okay, thank you very much. So.
Like we generalize that, so
Yeah.
phase transition will be on a circle.
Yeah.
Maybe it's, I mean, the fact that it's.
Yeah, the number of vacuum cannot jump.
Because we know the solution.
Theoretically.
Because we use the same EPS equation and in this language.
When you
In
compact
this
phi.
language, this means that phi is a function of C and
we know
phi bar is a function.
periodic quantity, which is surely.
It's the first
like,
one.
Yeah.
There's something about
Symmetry.
No, you want to put it, you want to.
Yeah, like with result, for instance.
No, but it was more.
I feel it's very close to here.
Well, the equation is the same.
No, I think the solution is.
The solution.
Then again.
The solution is the same, but
All the target something's not pure into one spring.
Yeah, because you have to
Yeah.
take into account energy density is different.
Nothing
because
to make it do, and
You have to take into account.
up the theory and to trust that nothing will happen even infinite mass when you reach the one. So instead of having some argument for pure and for.
Thank
There is such an argument. There is such an argument. You just work in a circle and then it confines on small circles, and then now you have to assume that everything is okay for us.
No. This is not correct. We know. All these arguments are about calculating a small and large radius. So two things. It's larger and it is. Because of the kind of one.
Precisely larger is very subtle. Precisely larger is very subtle.
But that I can buy, that you can define it properly there. But it's finite and there is no argument. What is there? You can have two bases in there. You can-
Sorry, do you want to understand what happens after you add a Gaugino mass? Is that the goal, or do you want to understand confinement that equals?
What I'm saying is. I thought what you want to say is that you take pure n equal 1 square meters, you put it on the circle and you show that there is confinement in small circles, so there must be a confinement in large circle, right?
Well, assuming there's no phase of difference.
Okay, but that's exactly the issue now. How can you argue that there is no phase transition? So there is no proof that n equal 1 square meters. What is it? There is an argument.
Like, if you computed the chiral ring system.
So what? It gives you the Gaugino condensate.
But you can calculate the
Gaugino condensate gives you, there is a Gaugino condensate. No, it doesn't mean that there is confinement. You can have symmetry breaking without.
But that's the thing. You can show that within index is already saturated on
So
small
within
circles.
index,
And then
the chiral backward, there are no deconfined backward.
What? There are two things, chiral, Gaugino condensate and confinement. What's the relation?
If the theory would be confined, it would mean that once you put it on a circle, there will be n squared backward, not n.
Okay, that's a different thing.
And
What
we
you're
can
saying is
compute
that.
the index.
I mean, you have to somehow argue that there's a phase transition in the size of the circle. This is very hard to believe.
No, there is no phase transition.
Yeah, I don't think there is, yeah.
For the Witten index, he proved that it's Q exact.
Yes, exactly. I mean,
The number of backward.
Okay, so the number of vacua even on R4, well, how the question is about R4.
But you could.
R4, you're saying
We know that there are n backward.
there are n vacua.
There's no there are backward quantum mechanics. No. So it's good.
What time does my talk start? Anybody know? 10 minutes ago.
I think the organizers are a little distracted.
I'm not an organizer.
They're arguing about QCD being confining.
The schedule become.
The schedule has been.
Is the
You know,
constant suppressed as well in this kind of theory?
I'll tell you, but yes. Well, it depends on what you mean by CC.
Yeah,
I mean,
they showed it in their papers.
I don't remember asking.
yes, I have to say that having seen how many talks in this workshop don't use supersymmetry, I feel stupid because I didn't have to talk. I thought I had to talk about something to do with something about Bose-Fermi cancellations. So I dragged this out from the, deep in the hard drive. Instead of talking about whatever mostly. But it's a fun story. It's relevant.
No, that's a very nice.
It's relevant. It's relevant.
It's the interesting is that.
It's just I haven't thought about it for like 2 years.
When Misha became from non-believer to a believer.
Yes.
That was
The
interesting.
timing was very good for me. It was like right before I applied to the job here.
Yeah,
I
he
see.
didn't believe this.
He didn't believe this. Yes, he
And
didn't
then he
believe this.
started believing what he
Yes,
was.
he didn't
Now
believe
he's a
it.
big supporter.
Misha very rather violently. Maybe.
You can wrote a paper that is.
I know.
There's a paper that.
We had some very vigorous exchanges.
Usually Soviet people never change their minds. So it's kind of.
No, it was good. It was actually really fun.
Many
Like,
times.
I still remember during one of our,
Is he convinced that there is no vacuum at the origin?
during one of our vigorous frank exchanges of views about all this, when I was a postdoc here, we were in a common area near Aleksey's office. Aleksey came out of his office and told Misha to go yell at your postdoc in your own office. I can't take this.
Was it say it in Russian?
Probably. Yeah,
Kamenev.
Yes.
Kamenev.
I don't remember what language.
He speaks Hebrew. Yeah, it was in technical.
Yeah, I think he was in, because he's right.
Yeah. Was how many years? Was not one. So he spent.
Misha, are you the session chair?
No. The session chair is.
Okay, I'll go.
Yeah.
That's it.
Yeah.
That's more in the whole country as well.
Well.
We have 70 per university, so 6 universities. And I want
So let's keep track of the delayed starting time.
Ah, wait.
He's actually invited me.
Dean of what? Somehow with the big fight and the big can't be big head. No, you don't deal with it like many like these are things you still know some parts.
I'll go and get him another ring.
By the way, I found this I wanted to forward it to you.
So basically, and early, I think that's really not an issue for.
Yeah.
Oh, I'm not planning on it, but should I finish at the?
No, you should definitely allow for time lost here, but let's just wait, let's give it a couple of minutes, see if people.
Ima nasceva lasciami
more encouraging.
וגם העלה לי את המסתור.
So 40 could take half an hour from here. So
about 3:50. Right?
Yeah. That's fine. 3:52.
Can you give me some warnings so I can?
Of course, I will. Okay, so our next speaker is Aleksey Cherman, who's going to tell us about Bose-Fermi cancellations without supersymmetry.
All right. Well, first, let me thank the organizers for inviting me to this fantastic workshop. It's really nice to be in Minneapolis. Right. So I'm going to tell you about work with many collaborators. But before I say anything about that, I want to start with an apology. I think I am by far the least supersymmetric person in this workshop. When I was preparing this talk, I thought that I only wrote 2 papers about supersymmetry in my entire life, one of which was very complex. But then during Emily's talk, I realized I forgot a paper. So in fact, it's 3 papers, and we all know 3 is a large limit. So I guess I'm much more supersymmetric than I thought. But actually, I'm not going to talk about any of those papers. Instead, I want to tell you something that's hopefully kind of entertaining about the supersymmetry-like behavior of some decidedly non-supersymmetric quantum fields. And connecting it to actual supersymmetry, or for that matter, to any deep symmetry principles or deep principles, is an open problem. So I should say that this work is with many collaborators who are all awesome, but I should note Misha Schiffman is one of them. And some of you may have seen some version of this talk before, but many of you have. So, I'm gonna try to make this as elementary as I can. So let's start kind of at the beginning. So in supersymmetric quantum field theories, it's really popular to think about partition functions, where instead of thinking about a thermal partition function, you insert a grading by fermion number. So these kinds of partition functions, they calculate things with different signs for bosons and fermions. And in supersymmetry, the whole raison d'etre of supersymmetry is to get pairings between bosons and fermions. And so these kinds of graded partition functions feature massive cancellations when you have supersymmetry. They're very useful. I should say that there's much more to supersymmetry than is encoded in just these particular graded partition functions. But that's all I'll actually need for my talk. And I should say something that everybody here knows, just so we're using the same language, in a compact, flat Euclidean space-time, the SUSY cancellations in this kind of object are so strong that these graded partition functions are typically just a number, namely the width of it.
But why it's so on Euclidean space-time? It's not just a.
Well, if you put something in, I don't want to talk, I want to focus on Euclidean for this entire talk, I should say, just for simplicity. And I put flat because if it's curved, it's
compactness not in space-time, it's compactness in functions. What is important.
Yes. So I know. I know. But generally speaking, this kind of object that has such severe cancellations, okay, it's a number, and it has no phase transitions as a function of beta, because it's just a number. Provided that you don't have the kinds of issues that Arkady just mentioned. Okay, so well, how much cancellation is there really because of supersymmetry? So there are many ways to think about that, but one of them is to take this graded partition function with a grading by fermion number and take beta to be small. Okay, and the reason to do that is that when beta is small, the circle size is smaller, the temperature is large. Any non-cancellations become especially manifest because like all states can contribute. Okay, and I'm going to assume that the theory of interest always has a mass gap. And imagine studying it on some 3-manifold times a circle. The circle is the sort of thermal circle, except that there's some funny boundary conditions on it so that you are counting states graded by their fermion number. And then in a 4D quantum field theory, you can do like a high temperature effective field theory argument that I learned from a paper by Lorenzo Di Pietro and Zohar to try to constrain the form of the log of the partition function for high temperatures. And it has to look like this, okay? So there's some term that goes like beta to the -3rd power. This is in 4 dimensions, which is basically like a cosmological constant like term. And then there's another term, which is beta to the -1st power, which involves the curvature of this manifold M. And then there might be some non-singular terms. Okay. Up to, and ignoring all subtleties about logs, which are not going to be important for what I'm saying. So far, this doesn't use anything about supersymmetry. Now, if the theory you're working with is actually supersymmetric, then actually this first term just vanishes. Okay, the vanishing of this term is closely related to the vanishing of the cosmological constant in theories with supersymmetry. And indeed, you can go and if you try to calculate C3, for example, the coefficient of this term, you'll see that it's basically proportional to the difference of the number of bosonic and fermionic degrees of freedom in the theory, in the UV, and in a supersymmetric theory, that is 0. And so this term will cancel. And that will leave this term, which would be non-zero if your manifold is curved, spatial manifold is curved. Lorenzo and Zohar showed that this you see in supersymmetric theories has some interesting relations to conformal anomalies. For me, that's not so important. The thing that I want to say is that this is kind of a 2D-like scaling for the partition function. So if you had some quantum field theory in D space-time dimensions, then the log of the partition function should suitably normalize, so it looks like a free energy. It should go like beta to the -t, if D is a space-time dimension. So getting beta to the -1st power over here translates to basically acting as if the non-cancelled degrees of freedom are somehow 2-dimensional. It's kind of interesting. So that's what supersymmetry buys you. And this much cancellation. At any point, please interrupt me with questions if you have any. Now, normally, people only study graded partition functions in supersymmetric field theories. Yes?
So Josh, I think I asked some version of this question before, but do I admit that, is it possible that phenomenon that you're about to describe can be explained still by SUSY because there's some hidden duality between the theory and some others.
I don't think so. So you mean the thing that I'm going to tell you?
Yeah.
I don't think so, but why don't you ask that question after more people can understand my answer? And well, okay, let's just say this way, if that were possible, I would be absolutely over the moon, thrilled, but I don't. I'd be very surprised, yeah. Okay, good, so nothing stops us from thinking about these kinds of gradient partition functions in non-supersymmetric theory. We can do whatever we want, we're theorists, right? We don't have to justify ourselves. But the question is it interesting? You have to justify why it's interesting. The thing is that if you don't have supersymmetry, then you don't expect Bose-Fermi cancellations to be. And then you would expect that this gradient partition function is some stupid function, which is very complicated, that depends on beta in some really complicated way. And indeed, without supersymmetry, if you think of beta as an inverse temperature, we know that you put the theory of finite temperature, typically you drive it to some phase transitions. Right? So most famously in Yang-Mills theory or QCD, there's a confinement deconfinement transition as a function of temperature. That really tells you that there are non-canceling things happening. Okay, so then, is there any hope of SUSY-like cancellations without supersymmetry? And I want to emphasize one more time, certainly not in general, no way. Okay? But there is a remarkable class of non-supersymmetric gauge theories, which does have SUSY-like cancellations that I'm about to explain. And they appear in the large N limit. And so actually the plan of the next few minutes is to first tell you why the large N limit should look like a terrible place to look for Bose-Fermi cancellations without supersymmetry. And having told you that, I'm going to try to tell you why it actually helps. So that's the plan. So let's think about some confining large N quantum field. Keep whatever you want in mind, Yang-Mills, or maybe something else. Okay, but that's the kind of theory that I'm going to be interested in. Okay, and one thing that we think we know about large N confining gauge theories is that they have a Hagedorn spectrum. So what does that mean? Well, if you write the partition function in terms of an integral over some density of states weighed by the usual Boltzmann factor, this is for the normal thermal partition function for now. The density of states is a function of energy. For large energies, it's an exponential growth in the energy with some scale called the Hagedorn, the inverse Hagedorn temperature, I guess, which goes like 1 over lambda QC. That's the expectation. Basically, there are various ways to argue for it, but the heuristic idea is that, well, you know, confining theories are really string theories, and string theories have Hagedorn spectra. That's the hand waving. And if you believe this, then you would say that as soon as, in this kind of integral, as soon as beta becomes smaller than this critical scale, you would expect some singularity in this integral, and hence a singularity in the partition function, and hence a phase transition. And that phase transition may or may not be at exactly this temperature, or maybe at a lower temperature, in principle, right? And that's exactly what happens in QCD. Before you actually manage to hit the Hagedorn scale, as you increase the temperature in Yang-Mills theory, you go through a confinement deconfinement phase transition, where the density of states just scales very differently than this, and that's the scaling that you get in quark-gluon plasmas. So that's been known since, well, more or less around the time that I was born.
Sorry, quark-gluon plasma isn't a deconfined state exactly. I mean,
well, in the real world, because of the quarks, it's very ambiguous to say what the heck is confinement. But if we just had a gluon plasma, then it is a deconfined phase. So for the moment, I am really, that's what I have in mind. And also at large N, I think that there's some heuristic sense in which the quark-gluon plasma really is deconfined at large N. At finite N, I don't know how to define anything. Okay. So the question that I'm going to try to answer is, can deconfinement as a function of beta be avoided? And if so, like, so what? Okay, I'm going to connect it to Bose-Fermi cancellation. So for that, you want to look at a different object. You want to look at a graded partition function where you count bosons and fermions with different signs, because that's an object that's more sensitive to possible cancellations. The other one isn't sensitive to that at all. Okay, so if you think it through, then this graded partition function, the thing that in supersymmetry would be the Witten index, but here it's just some random funny partition function. It's the difference of the bosonic and fermionic densities of states times the Boltzmann factor. For some reason, I had an oscillation notation. What used to be beta suddenly became an L. I apologize about that, but hopefully you're not too confused. Okay, beta and L are meant to be the same thing. So if
What is different? -1 to the power of implies this.
Precisely.
Formula, right?
Yes, exactly. It's meant to be an identity.
Yes.
Yeah, that's, instead, I used to have beta that denoted the size of the circle, now it's suddenly L. That's a mistake. I should just keep the same letter. Okay, so to avoid phase transitions, you would need to have enough of a conspiracy between these two things. And with supersymmetry, well, that's very easy because they're just literally the same for any non-zero energy. And then the cancellation is obvious. What about if you don't have supersymmetry? And here's where large N seems to be a very serious obstacle. You see, I told you about this Hagadorn growth that you expect because of confinement, but I didn't really tell you the full story. The full story is actually much worse. You expect that say the bosonic density of states is some exponentially growing thing in energy times some power series in energy with dimensions made up by like lambda QCD, maybe even logs of energy, also with dimensions made up appropriately. And then you would get some other exponential, which is less dominant than this one for large energy, and its own power series, and possibly also logs and stuff like that. And then more terms with, an infinite number of terms, in fact, with different growths, different rates of exponential growths. Okay? That's what we actually expect from confinement. Okay? And well, you expect the same thing for the fermions, generically. Okay? And then eventually you might get to something which doesn't grow exponentially for both the bosons and the fermions. And to avoid this large N Hagadorn-driven deconfinement, it has to be the case that you find some quantum filter that doesn't have supersymmetry, and yet all the red terms here and all the red terms here are literally identical. Okay? And then the only things that might not be identical are these things.
In general terms, you expect the exponents to be the same, you use the same letters.
Not necessarily, sorry, they should actually have different letters. You don't even necessarily know that they are the same. It's not obvious, actually. I'm about to argue that they are in some special case, but more generally, I really have no idea, no reason to think that.
So these kind of formulas hold for when the energy is less than lambda QCD?
When the energy is large compared to lambda QCD.
Large?
Yeah.
Oh, sorry.
Yeah, large. So this is like a large energy.
That's, we wanted before we're going to go through the Hagadorn transition.
He's investigating the hypothesis that there isn't.
You want me to say something, or is that there?
You're investigating the hypothesis that there might not be a Hagadorn.
I am, but I need to give evidence for it. So first I want to explain like why it's a bit surprising for such a thing to happen. It seems to require a truly epic conspiracy between an infinite number of terms, which normally requires things like symmetries, like supersymmetry. Okay. Yeah, so that's actually the next comment. So this degree of conspiracy between bosons and fermions probably is least fanciful without supersymmetry. And indeed, I want to emphasize this totally fails in large N QCD, like actual large N QCD. Because the only fermions in large N QCD or QCD are baryons, right? And that's only true if N is odd. And baryons get very heavy at large N. And so actually, if you look at this graded partition function for large N QCD, well, it's actually the same thing as a thermal partition function, because the only states that care about this -1 to the F have energies that scale like N. So in the total large limit, you don't care. Okay. So large N QCD is not going to be an example of something that has this cancellation without supersymmetry.
In large N QCD, you can say that fermions are kind of suppressed anyway.
Exactly. That's the point. They're very suppressed. You can forget them. They're baryons. They're very heavy. So if I'm going to have something with these funny cancellations, but then it can't be large N QCD, but maybe it's some other large N gauge theory. So I'm going to claim, based on a large amount of work, most of which is not even mine, that the interesting class of theories is actually adjoint QCD. So that's SUN Young Mills or UN Young Mills, it doesn't really matter for what I'm saying, I'm taking large N limit, with some number of Majorana fermions in the adjoint representation. And it's confining on R4 if an F is not too big. Exactly how big you need to have confinement on R4, nobody really knows, but that's the statement. Yes.
So if NF is 1, then isn't the theory actually? Oh, sorry, I didn't read this.
If an F is 1, then it's supersymmetric. But if an F is not 1, this is definitely not supersymmetric. Thank you very much. It's like I planted you in line.
Aleksey, is the demand for massless really necessary? Because suppose that you start with 5 flavors, And you
Oh,
give a
need some
mass.
of them massless. You need some of them massless.
Some of them massless, but suppose you start with 5 flavors and you start decoupling.
Then yes, that's okay. You
So
need
you can
need
even
at
have masses for the,
least- you need at least one flavor to be massless.
yes, but then the others can have masses.
Yes.
Why do you say that you need one massless flavor?
Huh?
You can deform the unknowns. What's the problem? It doesn't have a phase transition.
Eventually it does. No, so. Well, there could be chiral transitions. It could be.
We're about massive, all massive. Never mind, it's irrelevant for your talk, I'm sorry.
So what does not, do you know for sure that, let's say NF equals 2, that you have at least one theory to which?
There's no, I don't know of a way to argue it in the continuum. I mean, it's with an F equals 2, you're very far from a loop. If you look at like a 2-loop beta function and you try to look for like to see if you're close to a Planck's X fixed point, it seems like you're very far. But do we, can we trust that? I don't know. You need to do lattice calculations. They're pretty hard, and I don't think that there's like super persuasive evidence.
Your hypothesis.
My hypothesis is yes. Not super persuasive, but by the time you get to N equals 5, it kind of seems very likely that you're IR conformal. So N equals 4, I don't know.
There was supposed to be a talk by Thomas Dumitrescu about such a model. I think his conclusion is.
It was about NF equal 2.
It's NF equals 2, but at finite n, I think, and I think the jury is out about exactly what happens to their story as you reach real adjoint UCD. At least that's what I gathered from one of the collaborators. Yes, that's what I gathered from Emily's talk and Thomas's talk a couple of weeks ago. All right, so adjunct UCD has lots of light fermionic states for any NF. For example, you could take a state like this. So here lambda is one of the fermions, and A is a flavor index, and that mimics a fermion out of the vacuum. That does too. But there's no supersymmetry when an F is greater than 1, because if you look microscopically, there are this number of bosons. The 2 comes from the polarizations of the gluons. That's the number of gluons. Color, but there are that many microscopic fermions, and when an F is greater than 1, they don't match. So this theory cannot be supersymmetric. It's not supersymmetric. Okay. So let me make a couple of weird claims that I'm going to try to back up. Okay. So the first claim is that the graded partition function for adjoint UCD doesn't have any phase transitions as a function of circle size when the circle doesn't scale with n at large n. So I should say that I think I mentioned it earlier, but this graded partition function is calculated by a path integral with periodic boundary conditions for everybody on the circle, including the fermions. And the absence of phase transitions in this situation was first advocated by Koptun and Salanyafi around 2007 for reasons that I'll explain momentarily. But since then, there have been many analytic and numerical lattice studies that support this contention. Okay, and I'm going to assume that it's correct. From everything I know it is. Okay? But the thing I'm going to emphasize here is that this observation made by Koptun and Salanyafi has a really striking implication if you really take it seriously at large n, which is that all of the Hagedorn divergences I mentioned earlier, they all cancel without supersymmetry. I'm going to try to explain that. And then the next claim, okay, is the following. So you might ask yourself the following question. What's left after these cancellations of the Hagedorn growing bits of the density?
And it doesn't depend on number of adjoints.
No.
Cancellation is always.
The cancellation is robust up until an F equals 6, where you at N equals 6, you lose control. You don't know what happens in the UV, and I don't want to.
And do you learn anything from integrating out the fermions to get to the n equals to 1 theory? Like, do you see a difference between finite n and large n?
I'll show you the difference between finite and large n involved. Yeah. Good. So, yeah. So the naive guess would be that after these cancellations, you have some few degrees particles, like a few particles worth of 4d degrees of freedom left, which would translate to this kind of density of states, which translates to log of the partition function, which for small beta grows like beta to the -3rd power times the volume. Okay. And the claim is that actually you get at most a 2D density of states, because you actually get this kind of growth instead. Okay, just like in supersymmetric filters. Yes,
Maybe you're talking about Largen, I don't know.
yeah, large N, that's what I mean, yes.
But the paper of Clay and Thomas and Emily, and they showed that there is CP1. So there are ghosts in bosons for an equals 2. So certainly there should be some pressure or like contribution to the partition function, which goes like volume.
I'm not.
That's from this, 2 degrees of freedom. Maybe you.
That's an interesting comment.
And that part is purely bosonic, so there will be no constellations.
That's it, low temperature.
Yeah, but at low temperature.
Let's return to that. Let's return to that. That's,
There is a single model at low temperatures.
Isn't that supposed to be high?
yeah, that's a, well, there shouldn't be,
We claim that there is not.
there's no phase transition, but so the statement is about a small beta, not large beta. So that, so large beta is where that CP1 is relevant, but this is small beta, so there.
Symmetry is restored, okay.
Well, I'm confused actually.
So you said there's no correlation as a function of beta or for beta of order 0. So that's incompatible with Clay and Thomas's paper. And I mean,
That's peculiar.
You mean that there is
Let's think about it.
symmetry breaking?
CP1, yeah, there is a CP1.
Yeah, let's think
CP1.
about that one.
When you have NF flavors, you have symmetry breaking.
Yeah.
It's
Let me
Argyres
try to tell the
fermions, you
story
have
as I
symmetry
understand it,
breaking.
And then I think it's a very interesting
SUNF
comment. We should return and try to understand.
So you assume in the beginning of your talk there is a mass gap, right?
Yeah.
So there
Well,
are number goes on bosons. So why do you need to assume a mass gap actually?
Well, to do this high temperature effective field theory argument, it certainly helps assume a mass gap. Actually, if I work on a finite spatial volume, then there is a gap. So maybe that's important actually. So I think that maybe the rescues me, but I have to think. I think it may be self-consistent because I do eventually assume I'm a finite spatial volume. But let's think about it. Okay, so what I'm going to try to show, a few minutes remaining, is that in UN adjoint QCD in the large N limit, this coefficient right here goes like 1 over n squared. So if you take n to infinity with everything held fixed, then you just get this term. That was the original thing. So that means that the cancellations would be as strong as the supersymmetry. So why do I think this is true? So I think it's a consequence of staying in the confined phase for any beta, as long as the ferments are periodic. So here by confinement, I mean that there's an unrotating ZN1 form or center symmetry. For me, I mean just the center symmetry, and the center symmetry controls the behavior of polygon groups. So never mind what large N volume impedances or Gaugino reduction, this doesn't matter for me. But I'm going to try to explain why the center symmetry doesn't break in the context that I'm in, and then why this implies the cancellation I'm arguing. Let's warm up with Puri-Mills. In the high temperature limit, people have known for a long time that the partition function goes like 2 to the 4. Some n squared as a coefficient. So how do we know that actually? Well, we know that because Gross, Pisarsky, and Yaffe back around 1980 showed that the partition function at high temperatures can be related to the Polyakov loop effective potential evaluated at minimum. And that's an effective potential which you can calculate when the temperature is high or the surface the theory is on is small. It's just like a Coleman-Weinberg calculation. And here's the result. So it's got some prefactor which goes like 1 over the circle size to the 4th. And then there's some powers of the holonomy wrapping the convex. And the minimum of this potential is when the Polyakov loops are all proportional to the identity. So the center symmetry is spontaneously broken, there are n vacua. And if you evaluate what the potential actually is to get to the partition function, you recover the standard. So in Yang-Mills theory, center symmetry is broken whenever this one loop calculation is valid. Now, the question is, when is it valid? Well, it's valid when the circle size is small, because the idea is the polygon loop size is order beta, and when beta lambda is smaller than 1, much smaller than 1, lambda being lambda QCD, the quantum corrections to this one loop calculation that whose result I just advertised are small. It's meaningful to use that effective potential and compare its values at different minima. Thank you. And then you get the result. Okay. So things change dramatically in adjoint QCD with periodic boundary conditions, because then this is the form of the effective potential at one loop. Again, valid when the circle is sufficiently small. And so here's where the number of fermion flavors comes in. So this just flips the sign of the potential. So whatever used to be the minimum becomes the maximum, and vice versa. And so the new minimum of the potential actually has a preserved center symmetry. And this polyacouple loop has eigenvalues which are nth roots of unity. And all of its traces vanish up to the nth. Traces of powers of the polyacouple loop vanish until you take the nth power. And if you evaluate the effective potential on this minimum, you recover this result. So where it comes from is literally that most terms here give you 0, okay, because of this result. When little n is equal to capital NC, this gives you n squared. Okay, but that happens when little n is order NC. So this gives you 1 over n to the 4th. And overall, you get a 1 over n squared. So physically, this of course is presumably happening because of the plus and minus grading for the bosonic and fermionic states. But if you look at the individual quarks and gluons, what's happening, heuristically at least, is that they contribute with ZN phases due to this polyacouple loop that was in the previous page. That's what's giving the huge cancellations. So there's a way to think about that using kind of statistical mechanics-like ideas where you think of the eigenvalues of the polyacouple loop as being relatable to imaginary chemical potentials, but let me skip that. You can try to visualize these cancellations in a really calculable setting where we know everything about the partition function, namely on S3 times S1, where Haroni and others have calculated what it looks like, and we can basically borrow their results. It ends up being some rational function of, some infinite product based on some rational functions of the exponential of the circle size to the radius of some 3 sphere. And in this context, we know the entire spectrum. And you can see that if you plot the log of the degeneracies of the different states for bosons and fermions, they follow the same line. And so that after mismatching early on, because there's no supersymmetry, this is for 2 flavors. Okay. And that tells you that the leading exponential growth of the bosonic fermionic states is the same. But then you can also check that in fact all hagedorn growths cancel. You can just plot all of the singularities of the partition function when it's thermal, when you don't have any grading, and dots that occur between 0 and 1 on this plot are telling you about some hagedorn instabilities. Okay, this is with thermal boundary conditions for the fermions. And if you turn on grading, all of a sudden, all those dots disappear in this physical region, and there's no more phase transition. Now we've looked at higher loop corrections to the effective potential, and we don't think they changed the result. You can check this very explicitly at 2 loops, because people know the exact 2 loop effective potential for the polyacouple loops. But we also have an argument that it cannot change more generally in our paper, which I don't have time to get into. But one thing I want to mention is that non-perturbative effects can't change this, because they come with powers of, by construction, e to the minus 1 over lambda, basically, where lambda is the 't coupling. And that, by dimensional transmutation, is something like lambda QCD, and that cannot change the coefficient of beta to the minus 1/3. Beta to the minus 3. Okay. I think I am running out of time. So I had some comments on QCD in 2 dimensions, so maybe I should skip them. I should say the following. I don't really understand why this is happening when you really deep. it's conceivable that this is some kind of remnant of some misaligned supersymmetry in the string theory dual to QCD, maybe. Yeah, that's an idea in from the 90s in the context of fundamental string theory that was discovered by Kutasev, Cyberuk, and teams. I don't know. I mean, obviously, I don't know the string theory dual to QCD, and I don't know if it does have misaligned supersymmetry. So that's just a speculation. And I also don't know whether there's some sort of symmetry that explains this. If there is, it would have to be really exotic. So what I may or may not have convinced you of is that there exists some interesting class of non-supersymmetric field theories, which at large n must have some Bose-Fermi cancellations to be consistent with the results that I know about in the literature. And the cancellations have to be quite severe. So I hope that this is somewhat amusing and also hopefully somewhat confusing so that you're motivated to think about it and help try to understand what the heck is going on. Maybe there's some elegant explanation. That would be great to find. So I'm going to stop with this. Thanks for listening.
This had nothing to do with the Goldstone bosons that Zohar was at.
Yeah,
it was just the perturbative structure.
That's right. But that's the thing like if you look at height, the small beta behavior, right? The perturbative stuff is the thing that contributes to the beta to the -3. So.
But your claim is that the color singlets are the general.
Well, not that they're the general level by level, but there's some kind of on average cancellation.
Yes.
So Zohar, I think if you turn on a small temperature, like a low temperature, right, in the massless theory, assuming that it breaks chiral symmetry, the partition function will at low temperatures go like, t to the 4. But it's far from obvious why you wouldn't have that t to the 4 turn to some other power as you increase the temperature. It's some complicated function of temperature. So the statement here is about the high temperature limit of that. So it doesn't immediately seem to me that the comment about Goldstone bosons is fatal to what I'm saying.
But it implies what you're saying is that the Goldstone needs to have an almost degenerate Goldstein.
But the Goldstones may have partners that are heavier, but by the time you're at high temperatures, but they're not particular. Like you're not gonna imagine the would-be partners of the Goldstone bosons have a mass which is lambda QCD bigger.
That does not.
Well, by the time you're looking at high temperatures, who cares about lambda QCD differences? You're not gonna know.
At high temperature, there may be even no Goldstones, right?
Yeah. So in principle, yes, but if you really destroy the Goldstones, if you actually destroy them, then that would mean that you're restoring chiral symmetry. And the idea here is that you don't have phase transitions.
Anomalies would require Goldstones here to exist at every temperature.
Exactly. I would expect that they exist. I just think that they are matched by more excited states when you go to the high temperature. High temperature in quotes. Yeah.
Yeah, this is not point by point cancellation. This cancellation on average.
Yeah, it's sort of on average. Yes, exactly.
There is no even conserved supersymmetry color.
No.
You cannot write.
Yeah, I agree.
Maybe I can make a quick comment about theories that have holographic duals.
Yeah.
Even if they're not supersymmetric.
Yeah.
Namely, you can look at what the computation of trace of -1 to the f e to the minus beta h is in the bulk. And the bulk geometry that contributes to this quantity is a Kerr ADS black hole with complex angular velocity. And those black holes do have killing spinners on their geometry. Even if you study them in a gravitational theory, that's not supergravity. And their action is exactly 0. So that's the same action as that of thermal ADS. So from that perspective, in holographic theories, there's no Hawking phase transition.
Good.
So it's consistent with your.
Yes, I agree. That makes sense.
It's consistent, to be honest, because your geometry is a black hole, so it's deconfined. And his background is confined.
So it would be dual, like in the n=4 context, this would be dual to like not the ADS black hole, but the ADS solid.
He's saying that the minimum is deconfined. Non-minimum is confined.
Well, I'm saying that the thermal ABS and the black hole have exactly the same on shell action.
But
So-
who wins?
Who wins depends on loop corrections around around both.
So that's the
But the important thing is that there is no exponential growth in one over G Newton or exponential growth in N.
Okay.
So there is a very large cancellation in holographic theories.
So that leads to the key question. Define who wins in the holographic section.
Sure.
That's an interesting question. Sorry, which theories is this for?
Any theories, you just look at the Kerr ADS black holes, plug in angular velocity equal to 2 pi over beta. That's what 2 pi I over beta. That's what inserts -1 to the F as your chemical potential.
Isn't it known that it's the in the N=4 context, for example, that the black hole geometry doesn't actually contribute, and it's just the ADS, global ADS that contributes?
No, they both contribute. The question is which one is dominant, right?
I thought there was a paper written claiming that only the global ADS contributes.
To what? That paper is.
So not with thermal, with -1 to the.
That paper is wrong.
No, so good. So if you have thermal boundary conditions, they
That
both,
paper is
sorry,
wrong.
no, with thermal boundary conditions, they definitely both contribute, with thermal boundary conditions.
Yeah.
With the other boundary condition, I thought that only one of them.
Yeah, that paper is wrong.
paper
It's
is a
been
mistake.
revisited more recently.
Thank you very much, and I was not aware of that.
Yeah.
I should talk to you later. Yes. Thank you.
Okay, let's next Aleksey.
Is the theory confined?
Yeah.
It's a bit confined.
Degeneracy. Also, we didn't actually degeneracy. I don't know, I didn't. Probe such a thing. So we don't do a proper large M limit, like this is the kind of association as possibly and so like tests with the various small value.
Kind of comes. Our speaker today is Erich Poppitz, who's going to tell us about Anomalies, Tori and Gaugino.
Thank you guys for inviting me to this very interesting conference. I will talk about some recent work with Mohammed Tanger, and I will really bring you from the 50th anniversary of SUSY back to the 10th, take more or less, roughly speaking. And the title of the paper I'm talking about is this: is the Gaugino Condensate from an asymmetric 4 torus with a twist. And it sounds like a mouthful, so let me explain. Okay, so the source of this paper is twofold. The first part of the source are semi-classical studies of confinement. So this is related to the previous talk. And these semi-classical studies, I'll mention what they are in a controlled way. They show the relevance of objects of fractional topological charge for confinement and chiral symmetry breaking. And this has been advocated by many, notably by Tony Gonzalez Arroyo, but it can be shown in a control way in many situations. So the situations that I have in mind are the situations of a small circle, considering theories on R3+S1, where monopole instantons or twisted monopole instantons and various beasts made out of them can be argued to confine and lead to string formation and an area law. So this has been studied quite actively since 2007. It's pretty old stuff. And more new stuff is due to Tanizaki and Nonsal, who realized that if you compactify further with an appropriate twist in the T2 direction, you find confinement due to center vortices or wrapped center vortices. And these are also options that can be changed. So the heroes of this talk will be objects of fractional topological charge. And this setup, the setup of R3+S1, is interesting because in this setup, considering super young Mills on R3+S1, one of the 2 weakly coupled calculations of the Gaugino condensate was done. There are 2 calculations. One involves looking at SQCD, which then you use holomorphy to decouple the flavors and go to super young Mills in the large mass limit. And another calculation is directly done on R3+S1. And then you use independence of the size of the circle to argue that you obtain some value for the Gaugino condensate. And remarkably, the 2 calculations agree. In the old days, Misha remembers and other people remember, there was a controversy between the weak coupling and the strong coupling instanton calculations. There was some horrible difference of square root of 4/5, et cetera, et cetera. I think I got most people here, especially the presence in the audience. I missed our chairman who wrote a paper on N equal 1 star on articles S1, but it's not directly related to the Gaugino. Sorry?
It's very related. What they did is a special case. Very
correct.
special
It's
case.
correct.
No, but still this disagreement between strong coupling and weak coupling persists.
It is, but I think it's understood more or less.
No, it's the only thing which is understood that weak coupling is a better, weak coupling and then analytic continuation is much more, well, it is a reliable, but strong coupling is not so reliable.
So, so this was the first motivation of my talk and this long title. The second motivation is the more recent. You can say it's like 45th birthday of supersymmetry, is the realization that there are generalized symmetries, there are new backgrounds and new anomalies by these people, and it's quite an exciting development. And remarkably, within the development, two-form backgrounds for the one-form center symmetry also lead to fractional topological charge. And these days, I think the relation of tooth twists, which were studied a long time ago by Tooth and Bombal, to anomalies is quite clearly understood. So the purpose of my talk is really using this new insight on the right-hand side to revisit some old calculations from 1984 of the Gaugino condensate on a 4 torus. Okay, and we will find that it will not be completely satisfied with the answer, and you know, we'll point out to some possible resolutions. And one motivation for this calculation is to understand semi-classics in semi-classics better. You know, after all, it's argued that in this setup and in this other setup, R2 plus T2, which was displayed here, semi-classics was a good guide to the dynamics. And confronting semi-classics with supersymmetry is a very good idea because it keeps you honest. In a non-supersymmetric theory, you may say things, you may miss things, but if you have some supersymmetric results to compare to, it's an always good idea. And we'll see that it looks like something is missing in a situation where semi-classics should be valid. So this is my motivation. So let me start slowly. The main players of my talk is a 3 torus. So space is a 3 torus. And I studied with my students in 2021 the one-form center zero-form anomaly in Young-Mills and super Young-Mills in a Hamiltonian formalism on a twisted torus. So let me just summarize how the anomaly arises in this setup. So what one considers is a 3 torus. And one considers a Hilbert space with a tooth twist in the 1-2 direction. So this is the 1 and 2 direction, and there is the X3 direction, and there are twisted boundary conditions in the 1-2 plane. So in a modern language, this means that a 2-form gauge field gauging the ZN center symmetry has a non-vanishing integral over any plane which is in the 1-2 direction, and there are no fluxes. So it's just there are no 3-form fluxes, it's a topological background. This is equivalent to twisting the boundary conditions. In the presence of twisted boundary, when you consider the Hilbert space on a torus, the Hilbert space splits into the so-called electric flux sectors. And you can think of the electric fluxes as in many different ways. I will call T3 the generator of the center symmetry in the 3 direction. This is going to be particularly interested. The center symmetry generator acts on Wilson loops, which wind in the 3rd direction by a minus sign. So this is how it's characterized. So this is like center symmetry in thermal compactifications, except now it's in a spatial direction. Okay. And it's a symmetry, it commutes with the Hamiltonian. And so you can label energy eigenstates by eigenvalues of T3. Because it's a Z2 symmetry, the eigenvalues are mod n number. So states are labeled by this E3, which in SU2, which is all I'll discuss for most of the talk, they take value 0 and 1. Heuristically, you can think of these sectors of Hilbert space as being related by taking a Wilson loop in the 3rd direction, which is winding, and it takes you from this sector to this sector. Of course, it changes the energy because this is not some theory where there are real theories where Wilson loops come into the Hamiltonian. This is not it. Okay, so this is a theory where it changes the energy in general. Okay, and so the remarkable thing in super Young-Mills, which is my interest, is that in the SU2 super Young-Mills there is a Z4 chiral symmetry. So there is some operator that generates it, and it turns out that in this background, these operators of 2 symmetries, the center symmetry in the 3rd direction, the direction orthogonal to the plane with the twist, and the chiral symmetry, they don't commute. and they don't commute with a minus sign. And this minus minus, of course, is only non-zero if there is a twist. Okay, so we have a classic situation of two symmetry operators that don't commute with each other, but commute with a Hamiltonian. This means that the states are degenerate. And so in this case, if I label the state by the energy and the electric flux, the eigenvalue of T3, the chiral symmetry operator takes you from one flux state to the other flux state. Okay, and this degeneracy is true no matter what the size of the torus. All energy eigenstates of the Hamiltonian in the torus are doubly degenerate, exactly at any size torus. So this is a very rare situation in quantum field theory where this happens. Okay, so this is just the preparation. And now I'm interested in the Gaugino condensate. So let me define the following objects, which I will better motivate a little bit later. So I take the trace over this Hilbert space with a twist, -1 to the f, what Aleksey was considering, e to the minus beta h. I insert the Gaugino condensate, and I also insert a center symmetry generator in the direction, in the third direction, orthogonal to the twist. And I can write it as a sum over energy eigenstates labeled by the energy and labeled by the electric flux. And this T3 simply weights the states by a minus sign if the flux is 1. And then the interesting thing was that these states, all states were doubly degenerate. This operator of the chiral symmetry gives a minus sign when it acts on the Gaugino bilinear. And so if I insert this x dagger x inside the expectation value of the Gaugino condensate in some energy eigenstate with electric flux 0, it first of all, it produces a minus sign because x acting on lambda produces a minus sign, but then x acting on the 0 flux gives the state in a minus flux sector. So in these degenerate eigenstates, the Gaugino condensate has equal and opposite eigenvalues in the two states. Okay, and this is true at any size torus, which means that this expectation value really computes twice the sum of the expectation value of the Gaugino condensate in the electric flux states of one of the two flux sectors. And of course, it's weighted by the energy and -1 to the f. Okay, so this is the quantity that we're going to be computing, and we'll normalize it by a path integral or a trace without a twist in by T3, which is really the Witten index. So on the next slide, I have a different representation of this. This is just to remind people that if I consider a 4 torus, I have my twist in the Hilbert space of the 3 torus, which here is just depicted as a 2 torus. And this insertion of T3 in the path integral twists the boundary conditions in the time directions. It tells us that the gauge field at time beta is related to the gauge field at time 0 by the twist of T3. And when you have a gauge fields on the 4 torus with this sort of twist, the topological charge is 1/2 plus an integer, which was first argued by 't Hooft and then shown very carefully by Van Baal. So the quantity that I'm computing is the ratio of these traces interpreted in Hilbert space formulation. In terms of the path integral, I have a path integral with an insertion of lambda squared in the numerator, and the 2 twists of the boundary conditions are in the 1, 2, and 3, 4 directions. And in the numerator, I have a twist in the 1, 2, but not in the 3, 4 direction. And so this is my path integral representation. And of course, this is the quantity that I will be computing, the factor of 2 cancelled with the denominator. Okay, so this is from the previous page. So the reason I need this is that I'm going to do a semi-classical evaluation of this. And by what I said before, in the numerator, I am summing over field configurations which topological charge integer plus 1/2. In the denominator, I am summing over field configurations with topological charge 1. And so the natural question that arises is, I want to do a calculation. I want to do a semi-classical calculation. Clearly, you would probably agree with me that if I held the T4 small, the coupling never becomes strong. So semi-classics should be a good guide to whatever I'm doing. At least that's what we think. Okay, so we'll call this T4 the femto universe for following the guide. Okay? And so what we need to find classical configurations that have topological charge 1/2. Yeah, that's what we need to find. And it's also very nice with the index theorem that such configurations will have precisely 2 zero modes, which will saturate this integral. Okay, so the question is, what are these Q equals 1/2 configurations? Okay, it's a very interesting question, which was addressed by 't Hooft many years ago in 1981. And he wrote this paper, some twisted, he didn't say all, he said some twisted self-dual solutions for the Young-Mills equations on a hypertorus. And let me first read you from the paper. He said, considering the difficulty we had in finding these solutions, it was worth writing it up. Okay, so that was his motivation. And indeed, when he refers to the difficult, he refers not to the solution displayed here, because anybody could have written this solution. This is just a very simple thing that one can write. What is difficult is the SUN generalizations of this story. But I'm going to discuss the SU2. So these solutions are very simple solutions. So, you know, don't worry too much about it. They're solutions with a constant field strength. So the field strength is 2 pi over L1, L2, or 2 pi over L3, L4. And it's obvious that this is self-dual if the size of the torus obeys some relation. Okay, so this is what he found. And these solutions have some moduli which are appear as Wilson lines. And okay, so these are the moduli solutions. Okay, so we can try to use these solutions to calculate this Gaugino condensate on a small torus. And this solution is self-dual or BPS, so it preserves supersymmetry, is stable, etc. It's all very nice. So you try to do that. And so we attempt looking at this symmetric T4. And interestingly, everything falls apart. Okay? And the reason it falls apart is that when you start solving, for example, for the fermion zero modes, you find that there are 4 lambda and 2 lambda bar zero modes. So there are extra zero modes, and somehow this hasn't been discussed in the literature before. Of course, they obey the index theorem, but they're extra zero modes. These extra zero modes, they source the gauge field equation of motion. And so this is not a consistent background. They're expected to be lifted, but we don't know how. And also this limit, the symmetric torus limit, does not allow taking some interesting limit, for example, connecting to this Tanizaki-Yunsao semi-classical thing, which is very interesting from many points of view. Okay. So luckily, so this looks bad. Okay. Luckily, so I should say that Cohen and Gomez, so this is the 10 years after SUSY time that I'm, after the birth of SUSY, that I'm bringing you back to. Cohen and Gomez actually gave an expression for the Gaugino condensate on a T4 with these twisted boundary conditions, and using this torus solution. And they seem to be unaware of any of the subtleties that I mentioned. Okay, so they just write some answer. Of course, they did not compute the constant. And in any case, at that time, the Hilbert space on the torus, this exact degeneracy that I discussed due to the anomaly, it was not appreciated. So, so it would have been difficult to interpret the result. Okay, so this was the situation until recently. But luckily, Tony Gonzalez-Arroyo and collaborators actually proposed a way to construct BPS solution on a deformed torus when you depart from this symmetric torus relation. And on a deformed torus, in this solution, when you look at the deformed torus, when this is not obeyed, the BPS solution that you find, first of all, is not a constant F anymore. There is actually some structure. There is some hump that has a position that can move around. And there are only 2 zero modes, no 4 and 2 of the opposite chirality. There is no source terms in the equation of motion. And also, in principle, this allows you to take interesting limits. For example, this interesting limit by
generic exists for generic shape of the torus.
I will tell you. Okay, so this sounds fantastic. Okay, I did not tell you the bad news. The bad news is that the construction that these people proposed allows you to find a self-dual solution as an expansion in terms of the detuning parameters. So you take the difference between the symmetry parameter small. Okay, so there is a series which they argued as solutions exist to all orders. Analytically, it is not known if that series converges, but there is numerical evidence for SU2 for uniqueness and convergence. And this numerical evidence, of course, as anything numerical, you have to, ask questions about it. But people can take the lattice action and minimize with putting twists on the lattice is very easy, actually. Okay, so people know how to do that. They can minimize the action and they can find the profile of the solution on the lattice. And there is very good agreement with this analytical solution up to values of delta, which is almost 0.01. Okay, so it's not a terrible thing. Okay. So because of this evidence, which is only available for SU2, we will stick with SU2. And we'll just tell you what we get. Okay.
Can you say why is it important to have the explicit solution for the instanton? Usually we know the instanton action in general for a BPS instanton, and we also can see what the moduli space is. And we know the index theorem that tells us the general zero mode. So what are we gaining by having the explicit formula?
Very good. So So the first thing we are gaining is that these extra zero modes were lifted. You know, I did not know how to do the calculation with all these extra zero modes in there. So you would have to assume that they are lifted. The second thing we are gaining is the determination of the range of the. So in some sense, you're right, in the sense that when you have a BPS solution, you're calculating this lambda square quantity. All determinants cancel because of supersymmetry. In the end of the day, the calculation reduces to an integral over the moduli space. Okay, so you need to know how to integrate over the moduli space. And the way we fix the range of integration over these variables Zn, the moduli, is we use consistency. We require that the expectation value of any winding Wilson loop vanishes in the finite volume. That should be true. And in the end of the day, the integral for the Wilson loop reduces. Oh, this is, by the way, in pure Yang-Mills theory. Of course, you can do that in pure Yang-Mills theory as well. So you require that the Wilson loop vanishes. And
so why do you need a? Can't we do the ADHF construction?
Sorry?
Why do you need a consistency?
We need to determine the range of integration over the moduli of the solution.
Yeah, but the moduli space is fixed.
Sorry?
Don't you, I mean, don't you know the moduli space isn't it fixed by translational invariance on the torus? I mean,
The interesting thing is that in order for the Wilson loop to vanish, you have to integrate these variables from 0 to 4 pi. So roughly speaking, what this corresponds to, the instanton covers the torus twice.
This is strange.
It is, but
First of all, this is not an instanton, right?
it's a instanton.
It's a fractional.
Yeah, for those the moduli space.
No, it has 2 zero modes. It's a charge half instanton.
This configuration has
Yes.
two, but
Yes,
VPSTs.
it's correct, but I call it instanton.
Okay.
It has charge 1/2. The boundary conditions fix the charge.
I think
It's an SO3 in its bundle, right?
You can say that, yes.
But maybe these moduli spaces are not known.
Exactly. So the way we fix the range of this integration is by demanding that the Wilson loop vanish. And so this is how we decide that these coordinates are such that
you must have translation invariance. It must be,
we do.
there must be flat moduli spaces, right?
It is a flat moduli space. The moduli are these, okay, the moduli are these Wilson lines, and they persist when you deform the solution away from the symmetric torus. Okay. So the question is, how do we fix the range of integration? Naively, you could say that the z's should be from 0 to 2 pi, but that corresponds to shifting the centers from 0 to 2 pi.
Yeah.
But actually, vanishing of the Wilson loop tells you, and assuming uniqueness of the solution, both things tell you that you should integrate from 0 to 4 pi. So this is the step where we needed the explicit form. And this range is consistent with the fact that there are gauge invariant observables associated with this background, which distinguish all these different sets. Okay, so that's really the only place where the explicit form enters. It doesn't enter anywhere else. So when we do all this, I should go the other way. All this settles. Here's what we find. Remember, on the top is the quantity we calculate. We're calculating the expectation value of lambda squared in one of the flux sectors weighted by the energy, and all the qualifications are here. We have this is the states in the Hilbert space, it's a twist in the 1-2 direction. The volume is L1, L2, L3. L3, L4 minus L1, L2 is small compared to the volume, and all directions are small compared to lambda. Okay, so this is all being very honest. Okay, so doing this integral, as I explained to you, integrating over the z's from 0 to 4 pi, this is what we obtain with the definition of the strong coupling scale, which is the conventional one used in Misha's book, etc. Okay, and the interesting thing is that the result is 2 times the result on R4 and R3 cross S1. Okay. So that's our result, okay? And obtained with all these limits, okay? So there is an issue only, so to get to R4, what do you do? To get to R4, first we take L4 to infinity, then of course only the zero energy state contributes. And we obtain this answer. So this calculation gives the expectation value in the vacuum with the zero flux, again at finite volume. And then of course we have to set the volume to infinity in order to compare with the 4-dimensional solution. So if that can be done, then we have a problem because there is this factor of 2 difference. Okay, so how do we know we can do this? So we need some argument, for example, for holomorphy of lambda squared. And this argument seems to be readily available. If you take the derivative of lambda square we depend to lambda star, we get an insertion of this object F star, and then F is a supersymmetry transformation. F is the highest component of an antichiral field. F star is anti-commutator of Q with the middle component. Then you use the fact that lambda squared, which is the lowest component of a chiral superfield, commutes with Q. Then on R4, you would say that the Q annihilate the ground state. So this is the usual argument on R4 for holomorphy. On T3, you have a sum over energies, but for every given energy and every given flux, actually this expectation value also vanishes where it's averaged because the state form representation of the supersymmetry object. And so even on T4, you can argue that there is holomorphy. And so in the end of the day, we obtain the fact that lambda squared doesn't depend on lambda star. So this means that it's some constant on lambda cube and there cannot be any L lambda dependence. That's the argument. And by the way, it appears known or obvious to the authors of the solution of they're both here, solution of the anomaly puzzle paper, because they have an expression for the 4 Thoron contribution, which is precisely that C lambda cubed. They say it should be independent of L. It must have been obvious to you, okay, which it probably is, okay, because it's what it is. So we seem to have a problem, and there is various options. Okay, the first option is that we made an algebraic mistake. Okay, it's certainly quite possible, and this is why we spelled everything. Okay, it's a 70-page paper. Every factor of 2 is in there. Okay, you know, as people taught us how to do instanton calculations.
Sorry, can you say what the problem is?
Oh, the problem is that there is a factor of 2 difference.
Between what and what?
Between the calculation on R4 and R3 cross S1, which is given by this 16 pi squared lambda cubed, and the calculation that we obtained extrapolated, assuming L independence to the infinite.
But in one case, there's a Tuft flux inserted on a 2-cycle, and in R4.
Oh, absolutely, but it shouldn't matter in the infinite volume limit. That's at least what you think. Okay, because in the infinite volume, why would the boundary conditions matter?
Something could be sitting there. Because when you're integrating and imagine that your mode is kind of profiled in such a way that something sitting at the boundary, it happens.
Okay, maybe.
Yeah, no, I mean, I have in mind some particular examples.
It's still nice to understand what it is. Okay, so
It's for SU2.
For SU2, yeah. I'll tell you what we get for SUN, but there is caveats there. Okay, so for SU2 we get a factor of 2. Okay, so there may be a loophole in the Li independence, which is along the lines Arkady is suggesting. There could be other backgrounds because we used uniqueness of this background in an essential way to fix this integral. Yes.
This point that on the twisted torus, there is the confinement.
Yeah.
So there are 2 vacuum extra than the infinite volume limits.
You think so? Yes, maybe. Okay.
No.
Well,
The theory on the torus is deconfined with the center particles.
yes, but there is still okay.
So there are 2 twice more vacuum.
How can there be deconfinement?
Huh?
Why would there be deconfinement?
Erich proved that.
I did not discuss it here, but
I think this shouldn't matter.
yeah, I also think that it should.
Because I remember what we did with weak coupling. We fixed this theory. Okay. Then all gauge bosons are heavy, instanton is well defined. Everything is ironclad, and then we calculated the value of the correlator W trace W squared and trace phi squared. Okay, and it's fully saturated by 1 instanton, and it turned out to be certain constant times lambda to the 5th. Okay, and then we say it was X independent. So you can if you now split, you calculate. Also, what we can do, we know the product, and then there is the from Kanisha anomaly. It follows a relation between vacuum expectation of W squared times phi squared. So you know the product and you know the sum, you can find them separate. And this exactly coincided with later Jose and al calculations.
Just saying, when you take expectation value, sum over all vacuum, and there are twice more vacuum than it is in volume.
Yeah, yes,
So,
okay.
so Zohar, this is not included in this formula. So what Zohar is saying is actually something we're thinking about. So indeed, so this is saying that there are only the two vacua, which are the ones related by chiral symmetry. But there could be other two vacua which are related by the broken center symmetry in the third direction.
The way where this some coupling was wrong.
That could actually resolve it. Yes, thank you. Yeah. So anyway, let me continue. Maybe that's the resolution. It's definitely worth thinking about. If we do SUN, actually it's consistent with what Zohar is saying because we get a factor of n. Okay, so but I suspect that the SUN result is more suspect, and it's only a footnote in that paper for the following reason. This is the paper. I will just assume that I have time. Okay, so this I was planning. This is my last slide, and then I have conclusions. Okay. So I want to comment on these difficult solutions with n bigger than 2. So what Hoof did, this was actually the non-trivial part why he decided to publish that paper. So he takes twist 1, say in both the 1, 2, and 3, 4 plane. And then the way to construct, he constructs his solutions, he takes the number n, he splits it into the sum of 2 integers k plus l, both positive. And then what he argues is that for a KL symmetric torus, where the sides obey this relation, L times L3, L4 is K times L1, L2, there is a constant flux BPS solution of charge 1 over n, which would have two zero modes again to get the Gaugino condensate. And Gonzalez Arroyo generalized this small delta expansion to this case. And our result for the Gaugino condensate, which is n times bigger, uses any one of these. And the problem is that we don't have numerical evidence that this deformed solution is unique. And also, if you take L3, L4, and L1 and L2 to have generic size, you can take different K and L, and there are many ways to decompose n into sums of Ks and Ls, and those give different Q equals 1 instantons with different finite deltas on the same T4, and we have no clue if they're gauge equivalent or not. It's a very interesting thing that some mathematician or mathematically minded person should look at. But it's a fascinating system. So I say it would be nice to have a better understanding of what are these instantons and their modular spaces for SUN. We did the same thing for SUN as we did for SU2. We just took very small delta and we assumed that that solution is unique. So anyway, that's my talk. Okay, very simple. I told you that there are these weakly coupled calculations on R4 that seem to agree, and there is a calculation on T4, and we have a factor of 2 discrepancy, and maybe Zohar is right that that's the resolution. In any case, it would be nice to better understand these fractional charge instantons and their role in gauge dynamics, for which some evidence has been obtained. So that's my story. No, I've had it much worse.
The intuition is that it doesn't affect the boundary conditions, but there's some caveat to that. You were saying that there's some this I don't know about, this extra vacuum.
So what happens is that you can make an argument that the anomaly, yes, I need to write something about it. So if you consider Wilson loops extending in the, so let's say this. So if you have this torus, it's an interesting situation, okay, which and so here's the flux. You consider the correlator of Wilson loops in the 3 direction. So you consider in the direction of the flux. And if you consider the correlator of 2 Wilson loops in the 3rd direction at some position in the 2 plane, and at time 0 and another one. So this is the gauge invariant, is the trace. And W3 as the same position, but at some later time t. So you consider this expectation value. what you find is that it's non-zero as it goes to infinity. It's non-zero, so it goes to non-zero at any finite L1 and L2. And this is because of this double degeneracy at any finite torus. So what Zohar is saying is that there may be extra degeneracy, but I don't see the extra degeneracy. I'm just saying that this correlator doesn't go to zero. So the center symmetry in the third direction is broken at any finite size L1 and L2. Only in the limit when L1 and L2 goes to infinity does this go to zero. So this is the statement I can make. I don't know if it resolves the problem. That's where I stand.
So the extra vacuum you think are present for an arbitrarily large finite torus?
It sounds like.
It sounds like, yeah, I'm not sure. Not sure.
Yeah.
But, yeah.
It's okay, go ahead.
It's not directly about your work, but related to what Misha was saying. We, with Antonio Ritto, studied also lambda square condensate, starting from n equal to Zyberg-Witten solution. You put in one of these monopole dion vacuum, and then you add the, you add the adjoint maximum first, and then only this vacuum remain. And there you know the value of phi square, which is u, and then you use this anomaly relation. You get lambda, and then you do matching of this n equal 2 scale to n equal 1 scale. And the result is exact, actually. And this exact result coincides with what these people did this week instant calculation.
Sure, any consistent way of
It's exactly the same.
coupling.
What do you mean?
Any consistent way of deforming the theory to weak coupling, so you can do a reliable calculation
Yeah.
combined with holomorphy, preserving supersymmetry, must yield the same answer.
And we check this only not only for SUN, but also SO, USP, and it comes exact. So I don't know.
This maybe is different because of the twist.
Yeah.
You have?
I'll ask private.
Okay, let's thank Erich.
So I don't think it's such a vector because this non-vanishing is based on this exactly degenerate vectors.
You know, it's not a complex parameter, right? We analytically continue with there.
Yeah.
And we put the complex parameter. We move that. Analytic proof.
Yeah.
That's what I was saying.